All right, good morning, everybody. Can you guys hear me okay? Well, let me turn on the video too. Hopefully you guys can hear and see me, hopefully. Oh, and I also forgot to share my screen. 2 seconds, guys. Screen one. Perfect. So I got a yes in the chat. Good to go. How are you guys doing? How is the class doing? I was going to say it's getting warmer outside, but the last couple days have proved me wrong, which kind of sucks. But hey, it's March. Should only get warmer, right? Hopefully. This is Canada, so it's always kind of a wild card, but hopefully things will get warmer and everybody's lives gets a little bit happier. I know personally I like the summer myself, so I can't wait for it to get a little bit nicer outside. I'm also just going to shut the curtain here so it's not so bright. And yeah, so how are you guys doing? Any takers want to answer the question or no? Don't want to answer the question? All right. Well, I hope that you guys are all doing well. Hope you've been having fun so far in this course. As I kind of mentioned last time, this is the day where the course kind of takes a little bit of a shift, and you guys are going to see why exactly that happens. Up until this point, we've mainly been concerned with theory. And the reason why is because we've been dealing with linear analysis. Linear analysis, it's by no means easy. As you guys have seen, we've gone to some quite complex topics. But it is easy. It's on the easier side of things when we compare it to actual realistic scenarios. So that's why we were focused on the theory. It gives you guys a good background of what exactly ABAQUS is doing in the background, or ANSYS, or whatever program you guys want. And that's what we're really trying to do here is we want you guys to understand, all right, I have my finite element program. I can throw a bunch of inputs into it, but we were really trying to figure out what do those inputs mean. And I think by this point, you guys, for the most part, have a good understanding of what exactly those inputs mean, and that was all for a linear analysis. Now, of course, real life, not really a linear analysis. We have something called a nonlinear analysis, which is the complete opposite, and this makes our lives a little bit harder. So from this point on, we're going to be focusing on this nonlinear analysis, and since the math gets quite complex, we're going to focus more on the implementation of this nonlinear analysis into a program like ABAQUS or ANSYS, rather than focusing on the theory. And the reason why is because the theory gets quite complex. It would actually take quite a while to teach, which is kind of a problem. I've talked to Dr. Samir Adib about trying to create another Civi course dedicated to this math, this plasticity math, stuff like this. So it's something that we might explore in the summer. I'm not sure if you guys would be interested in it, but it's something that could be a lot of fun. So before we begin today, I'm just going to jump on over to E-Class. So can you guys see E-Class? I'm hoping that you guys can see E-Class here. And we're just going to do a quick rundown of what's to expect in this second half of the course now. So today we're going to be discussing the Newton-Raphson method. As we're going to see today, these last four lectures, the last four lectures, they all address basically a nonlinearity type. So today we're going to be discussing the Newton-Raphson method, which is kind of our get-out-of-jail-free card when we're discussing geometric nonlinearities, for the most part, and we're going to discuss why later. Lecture 8, which is next week, we're going to be discussing material plasticity models. So that plasticity model, this basically will start taking into account the nonlinear behavior of the materials we use. Of course, when we're talking about steel, it's not just elastic. We know at a certain point it's going to start to yield, and then the behavior becomes much different. And then when we look at concrete, it's an even bigger shit show in the fact that it's basically parabolic in compression and linear in tension, but in tension it starts to crack. So the material actually starts to degrade, which isn't fun at all when we're looking at it from a math perspective. Lecture 9, we start talking about constraints and contact. Of course, it's very rare that we're dealing with a scenario where we just have one beam, one bar, one of anything. We usually have multiple parts interacting with each other. So we need to figure out, okay, if I have two parts and they come together and make contact, well, I have to define the contact between them so that they can react off of each other and maintain a new sort of equilibrium. In ABAQUS, we can define those two parts. You guys can do it right now if you guys want. But if we don't define that contact and we push them together, they're just going to go right through each other. Of course, that's not realistic. Things just don't go right through each other, so we need to figure out what that is. And then finally, lecture 10, we're going to talk about instability. So this would be things like buckling. So this goes back to the geometric nonlinearities that we're going to be discussing today, but buckling is kind of a special case. So we're going to tackle that separately in lecture 10 there. And that's going to basically wrap up this course. Now, again, for the last part here, since this is going to be very math heavy, we're going to focus more on the implementation of these nonlinearities into our finite element program rather than go into the math itself. We're going to kind of briefly explore the math, but we're not going to really get into it, if you guys know what I mean. Now, if we look at the lecture content, there is room for a lecture 11. Now, what I'm going to do is this, is we're going to have a lecture 11. I'm not sure if it'll be in person, but basically what I want to do with lecture 11 is just figure out what you guys want to know, because the finite element program is so broad. We have mechanical engineers, we have chemical engineers. We're not going to be able to explore all the topics of the finite element program in this course alone. So what I would like to do is, if you guys want a certain something maybe explained, message me and then I'm going to start creating slides. One of the things I'm definitely going to create for this lecture 11, which again will probably just be me posting a bunch of slides and a bunch of YouTube videos, but it's going to be beam elements. Notice that we didn't talk about beam elements. If we scroll up here, we talked about bars and trusses, and then we went right to solid elements. Why do you think that is? Question for the chat. Why didn't we explore beam elements? I want to see if you guys have been paying attention. It's just a very little part in one of the slides that kind of hints why we didn't explore beams, but I'm curious what you guys think. Why do you think we didn't explore beam elements? Any takers today? It's definitely a difficult question. And it's the same reason why we're not exploring shell elements either. Shell elements will also be covered in this lecture 11, but again, we're not exploring them in the main lectures, and there's a specific reason why. No one wants to try and answer? That's okay. Basically what happens is when we're dealing with those bar elements as well as our solid elements, we said that they are C0 continuous, meaning that as long as the displacement is continuous between elements, I'm happy. I don't care if the stress derivatives are discontinuous or anything like that. As long as that displacement was good, I'm good. What happens in beam elements, and what also happens in shell elements, is they have that rotational degree of freedom. Now remember, when we were dealing with these solid elements in ABAQUS, a lot of you guys said I need to restrict the rotation. But I said, well, it's actually kind of a trick, where these solid elements don't have that degree of freedom associated with rotation, so we don't actually need to restrict it. When we deal with beam elements and when we deal with shell elements, they have that rotational degree of freedom, and that adds a lot of complexity into our basically our theoretical formulations. What happens is those are actually C1 continuous, which means that not only is the displacement continuous, but the rotation field also has to be continuous. Therefore, the formulations of those elements, they get a little bit messy. So those are one of the formulations that I'm going to show you guys in lecture 11, but it won't be covered on the final exam, anything like that. So just something to kind of be aware of. Now, those are those remaining lectures that we have. Newton-Raphson method today, material plasticity next week, constraints and contact, and instability. Now, let's look at the assignments. So when we look at assignment submissions, we see that there is a total of 9 assignments. Now, this kind of always bothered me because, well, it's 9. It's like, you know, when you stop the microwave at even intervals, or you turn up the volume on a TV at even intervals? Well, that's what I like for my assignments, but the problem is because we were doing basically review of linear algebra, I didn't really give you guys a linear algebra assignment because, again, it was just review. So that left us with 9 assignments, but I want 10 assignments. So here's what I'm thinking. And this is going to be a democratic process. I'm going to ask you guys what you think, and if you guys like it, you guys say yes. If you guys don't like it, we'll stick with 9. But what I'm thinking is this. We're going to have an assignment 10. And assignment 10, everyone will get 100. And the reason why is because assignment 10 should have been this. Because this is what I got the most emails about. Assignment 10, you get 100% for installing ABAQUS. One of the things that I noticed that thus far, that was the hardest part of the course, installing ABAQUS. A lot of you guys got clapped by IT so hard. So what I'm thinking is, you know what? You guys did good effort installing ABAQUS. We'll make that an assignment and we'll give you guys all 100% for that assignment 10. Now, again, this is democratic. You guys can tell me what you think. Do you guys want that where you guys all get 100% for assignment 10 for your efforts in Abacus? Or do you guys just want to leave it 9 assignments? What do you guys think? Up to you guys. 10th assignment? All right. Sure. All right. So 9 is fine. Ooh, this is going to be real fun. All right. So you guys can email me too. For the most part, it looks like we're going to go with those 10 assignments. But if one of you guys is saying, you know, Clayton, I'm not comfortable with this, just send me a message and we can figure it out. So don't worry too much. So that is the assignments. Now, final project. This is one of those things that I'm starting to get emails about, which is good. So final project is something that you guys should definitely start once you guys have time, because as you're going to see, once we start talking about a nonlinear analysis, it is basically almost a trial and error process. You guys are going to try some things, may not work. You guys are going to try some new things, may not work. You guys are not always going to get good results on the first try. And specifically in nonlinear analysis, you guys will probably have it diverge the first try, meaning you won't get any results at all. So it's definitely a trial and error process. So you definitely want to start as soon as possible. Now, I got a good question of how much should I do per week? And this is what I recommend. At this point, when you guys are looking at Abacus, and we're going to talk more about special shapes today, so don't worry. So by the end of this lecture today, we will know how to basically create the geometry of our model. And in addition to that, we're going to talk about how do we account for these nonlinear geometric effects. So by the end of today, you guys can create your model's geometry and then throw in the nonlinear geometry. That shouldn't be a problem. So what I recommend is basically follow along with the lectures. Next lecture, we're going to start talking about material plasticity. So if you guys have some plasticity in your model, maybe by the end of next lecture, you guys throw in the plasticity. After that, you guys say, you know what, I have some contact in my model. Well, after lecture 9, that's when you guys can address the contact. Kind of follow along with the lecture would be my personal recommendation. Because by the time we're done all 10 of the lectures, your guys' model should be kind of good to go, ready to run sort of deal. And then you guys can fine tune it. Maybe you guys used 4-node reduced integration elements. Maybe it diverged. Maybe we try 4-node without reduced integration. And some of you guys may be saying, you know what, maybe I'm going to go 8-node. Really make sure that that accuracy is there, etc. So that's what I recommend for the final project. Now, the last thing we're going to talk about is the final exam. So do you guys want to talk about the final exam, or do you guys want to put it on the back burner and try and forget about it until as late as possible? What do you guys think? Should we? Yes, please. Perfect. So the final exam, as I'm doing the lectures, it's starting to come very clear on what I want to do. So the final exam is going to be take-home exam. All right, take home. And I'm going to give you guys, I'm thinking 5 days to complete the exam. 5 days. All right, so it's not going to be a rush. And now you guys are thinking, oh shit, he's given us 5 days. It's going to be brutal. Well, it's actually not going to be a brutal exam. The reason why I'm giving you guys 5 days is this. You guys are graduate students. You guys don't just have my class to deal with. You guys have other classes. You guys have family commitments. You guys have research commitments. I know that supervisors are usually on your ass at this point in the semester to try and get some results, something like that. So what I want to do is I want to give you guys an exam, and I want to give you guys ample time to complete it without trying to risk your other commitments. So what I'm thinking for the date is the following. So we're doing lecture 7 today. 8 on the 8th, lecture 9 on the 15th, and then lecture 10 on the 22nd. Now, this is going to be that lecture 11. Now, lecture 11, again, that won't be on the final exam. It'll just be kind of for your benefit only. So what I'm thinking is this. We have the final exam on the week of the 5th. Now, I know that it's technically Easter on the 5th, but again, you guys will be given the whole week. So what I'm thinking is I'll release the exam Sunday night, and I will make it due Saturday morning. Now, how does that sit for you guys? How does that look? If I were to release it April 4th at night and then make it due Saturday the 10th in the morning, does that sit well with you guys? Or are you guys thinking, you know what, Clayton, I got something to do? What do you guys think? Preliminary, of course. I know things will come up between now and then, but how does that? It looks good for now? All right, so hopefully that's good for you guys. That's, again, preliminary. I'll send an email out with these specific dates, and I'm just going to make sure that it kind of works for everybody. Perfect. All right, so now if we're talking about the questions in the final exam, I'm thinking this. I'm thinking 5 questions. All right, each question is going to be worth, let's say, well, it'd be worth 20%. So I'm going to have 5 questions. Each question will be equal in weight, something like that. If you guys can just do 1 question per day, you guys will be done the final exam, no problem. But of course, I'm going to make the exam such that if you want to complete it all in 1 day, you can. I'm not going to make it a mandatory 5-day brutal assignment, or I guess final exam. I'm going to try and make it nice and fair to you guys, of course. So that is everything I want to talk about when it comes to E-Class. So right now, is there any questions or concerns about the course content and where we're headed, final exam, project, assignments, anything like that? Does the final exam have coding? So Mathematica will be of benefit in the final exam. That's all I'm going to say. Technically, you guys can solve everything that'll be in the final exam by hand. Okay, I'm not going to make it so that it is impossible to do it by hand. I will make it so that you can do it by hand if you guys want, but yeah, that's it. So Aslam says, will the assignment date remain? What assignment date are you referring to, my friend? Are you talking about the project or these assignments? Because these assignment dates right here, these are all static. These will not change. Project. So yeah, the project date is also going to be the same. If we look at our project submission box, this is the date that it is due. Friday, April 16th, 5 p.m. And the reason why, that's the last day of class. So that's not going to change. If I were to change it, then I have hoops to basically jump through if you're ever trying to get a project that's due after class technically ends, something like that. I think it's nice because by the last day of our classes, you guys will be completely done this course, which I think could be a benefit for me, benefit for you guys. Everybody wins. All right, so I got a private message about defining cracks in the theory or in ABAQUS. Now, cracks is a bit complex. So what we're going to do when it comes to cracks is this, is in concrete damage plasticity model, which we're going to discuss here, we're going to talk about how the tensile behavior basically accounts for the cracks. But showing the cracks in a finite element model, it's actually not very, very simple. What we technically do is we go to other methods, because if something is cracking in the model, it basically means that our mesh is breaking apart. And we have to account for that fact that, yes, our mesh is breaking into pieces. Now, what typically happened in the past is when our mesh breaks into pieces, you would remesh the object. So as your analysis ran, you would remesh the object over and over again. You would apply a load, remesh the object, apply a load, remesh. But there's actually been some very nice, I don't know, advancements, I guess would be the word, called XFEM, which allows us to display those cracks. And we're going to talk about that a little bit in concrete plasticity, but that is kind of more of an advanced topic, if you will. So if you have any questions, let me know by email and we can try and figure it out together. But no, it's a good question, and it's something that we'll definitely talk about. And it's something that maybe I had planned for the final exam. So it's, again, very, very good question. So other than that, I don't see any sort of other questions. We are going to start today's lecture. All right, well, almost start today's lecture. So I'm going to exit out of E-Class, but instead of getting into this Newton-Raphson method, well, let me move this over here. What I would like to do with you guys is I'm going to share this drawing screen. All right, can you guys see the drawing screen now? I'm not too sure. This thing over here, is this what's being displayed, this black screen? Yes, perfect. So what I really want to emphasize to you guys, and I've already talked about this, is by this point in the class, you guys know how to do a linear analysis, which is quite remarkable. So pat yourselves on the back, give yourselves a little award, something like that, maybe order a pizza and celebrate. At this point, you guys can do a linear analysis by yourself. You guys don't need ABAQUS, you guys don't need anything else. It's actually not too bad. So what I would do is, if I were to give you guys this right here, a beam like this, and let's say that it's exactly the same as your assignment. So let's say that this right here is fixed. So nothing too crazy there. And let's say that I apply a point load over here. If this was kept as a linear analysis, you guys can all do this. This is something that is not beyond your capabilities right now. The first thing that you guys would have to decide is, okay, how am I going to split up my geometry? So maybe if I'm looking at this and saying, you know what, it's kind of rectangular, I'm going to use rectangular elements. Maybe I use 4. So maybe I divide it down the center, I go across like this, and I have 4 node elements. So I'm going to have a node here, I'm going to have a node there, here, 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 and then finally here. So 4 elements, each element has 4 nodes. Now, we also know that each element is going to have a stiffness, which we call Ke. Ke, Ke, and finally Ke. Now, my question to you guys, because this is going to be nice and interactive today, just the way you guys like it, do we know how to figure out what that stiffness Ke is of our element? What do you guys think? Do you guys have the tools to figure out what Ke is? Our element stiffness. Yes, yes, yes. So you guys, Ke, that's not a problem. Now, if we know the stiffnesses of all 4 of those elements, we know, can we create our global stiffness matrix? Do you guys know how to do that? Yes? Perfect. Yeah, exactly. So we take our element stiffnesses and we create our global stiffness matrix K. And what's nice about a linear analysis is we can do this kind of independently. And this is going to be why linear analysis is so easy, is we can do that stiffness matrix kind of independently all by itself. Now, if we were to look on the other side, if I were to say, well, I also need my nodal forces. Can you guys figure out what our nodal forces are? What do you guys think? Can you guys figure out our nodal force vector? I hear another yeah. Exactly. Our nodal force vector is basically going to have 3 components. All right, 3 components. So this is equal to a nodal force vector due to gravity or those body forces. So remember that the body forces was that integral of rho b times n transpose. So that's not too bad. We said that we also had a force vector due to traction, or traction vectors. And again, you guys may be always confused what exactly is a traction vector. Well, traction vector, let's switch to a different color. That's if I were to have, let's say, a distributed load acting on our beam. So if we had this distributed load right here, what that traction vector does is it takes that distributed load and creates 2-point loads at our node. So those come right from that big ugly formula that we're so used to seeing. That n transpose times rho b and then n transpose times tn. That's something you guys have seen. But then we also have a third component, which we don't really talk about enough, and I call it Fa, which is our applied force. So this force right here, this is something that we apply directly to the nodes, so that would go in that part over there. And if we were to take a step back and look at that, that basically accounts for all the loads we typically see in structural engineering. We have point loads, which would go in Fa. We have distributed loads, which would be considered a traction vector. And then we have self-weight, so forces due to gravity or body forces, which would go right there. But in the end, we have formulas for all of those, besides Fa, but Fa, of course, is simplistic. It's just the load at the node. So we can find out what exactly our nodal force vector is. Now, after that, we can say, all right, well, we have a nice equation here where we have our global stiffness matrix K multiplied by our nodal displacements U. This is going to be equal to our force vector F. We know what K is. We know what F is. Therefore, we can solve for what our nodal displacements are. And then, of course, after our nodal displacements, we have our approximations. So with those nodal displacements, we can approximate the displacement in the element. We can take the derivative, find the strain in the element, use our constitutive law to find the stress in the element, etc., etc. So at this point, if I were to take a step back and ask you guys, do you guys know how to conduct a linear analysis? What is going to be your answer? Yes, exactly. We just covered it. Now, the thing that I really want to emphasize is this. Right now, when we were doing this linear analysis, could we calculated K first in this theoretical scenario, but could we have calculated F first? What do you guys think? Does it matter if we do our stiffness first or if we do our nodal forces first? So Aslam's right. We could have calculated at first. It doesn't matter in this linear analysis whether we do our stiffness matrix K first or our nodal forces vector F first. The calculations are independent. We can kind of do whatever we want. As we're going to see in a nonlinear analysis, everything is dependent on each other. And this is where kind of the problems start for us. All right, the problems start. So this was just a hey, how you doing? Now let's get into the fun of today's lecture. And again, today we're going to start taking that shift where we are going to, and let me just share my screen over back to the other side, where we're going to start addressing some of these nonlinearities. So today with this Newton-Raphson method, we are going to get into a little bit of theory. I said that the theory is going to start to diminish, and it's true, but there's still going to be some theory, so you guys know what exactly ABAQUS is doing. And I don't want animations, I want to start the slideshow. So let's begin. This is your guys' topic into, or I guess your first steps into nonlinear analysis. So buckle up, it's going to be a bumpy ride. So let's talk about linear versus nonlinear analysis. At this point, as we just discussed, linear analysis, you guys are thinking no problem. Clayton, that's a baby analysis. I can do it, no problem, easy peasy. And why is it easy peasy? Well, we had this. When we were deriving our equilibrium conditions for our solid element, we basically had this formula, and then we were able to use a bunch of assumptions, linear elastic assumptions, to basically create this formula that you guys now know and love. Now, we made further modifications to this formula in the fact that we dealt with those integrals. So instead of just B transpose C times B, we now have a determinant of J, and then we know that we're integrating from -1 to 1 in both directions. So this is still the more general form, but you guys know where this equation basically comes from. It's nice and easy. Now, if we were to look at this equation, we say, all right, well, this was our stiffness matrix. That was no problem. And we said that this was the two components of our nodal forces. Now, again, this component right here doesn't have our applied concentrated loads at the nodes, but those are also easy just to kind of tack on. So we basically have our stiffness multiplied by a displacement vector is equal to a force vector. And that's exactly what we did back there. We figured out what our stiffness was, we figured out what our nodal forces were, and then we solve for our nodal displacements. And this is why you guys are thinking, Clayton, baby analysis. I can do this in my sleep, no problem at all. But now we have to kind of take a step back and say, how did we get to this point? Well, we basically made two assumptions. We made a lot of assumptions. It's more than just two, but we made two very big assumptions. Very big assumptions. The first one was small deformations. Small deformations. And as you guys have seen, assuming small deformations isn't always the best. Remember when we did the assignment and we rotated that rectangle, or that plate, whatever you want to call it, we rotated it. Now, when we do rigid body rotation, I'm not straining anything. If I were to take my little clicker and I'm just rotating it, I'm not straining it. It's not in tension, it's not a compression. All I'm doing is rotating it. But due to our small strain matrix, we actually predicted some strains, especially once we got into large rotations. And we know that this is actually incorrect. So this small deformations kind of bites us in the ass because we're limited now to very small displacements. Now, when it comes to civil applications, most of the time, this is true. All right, most of the time, this is true. We don't want our building displacing a lot. This would make people kind of be very scared. No one wants to be in a building when it's going crazy. But unfortunately, there are some events where things will go crazy. For example, an earthquake. When we have an earthquake on a building, the building is not exactly static. It starts deflecting a lot. So we have to actually take that into account. Now, if we were to assume small deformations with an earthquake, well, I'm sure that all of my South American friends are laughing at me right now just at the thought of that. It's not a very good assumption. Now, I'm actually curious. So again, I'm civil. The course is civil, but we have a lot of mechanical engineers. To my mechanical engineers out there, how long would that small deformations assumption last you? Are you guys typically dealing with small deformations, or are you guys typically dealing with large deformations? What do you guys think? Or not think, because this is more of a curiosity of mine to you guys. What do you guys typically deal with? my mechanical friends out there. Both, exactly. And that's one of the nice things is we deal with both. So if we're dealing with these small deformations elastic, we have a nice easy solution. But we also need to create a solution for when we have those crazy scenarios. It's the exact same thing with civil. We have our nice equation if we're dealing with a nice linear elastic problem. If I were to deal with a building under normal everyday loads, the assumption of linear elasticity, small deformations, those are good to go. Again, it's only those kind of crazy loads that we have to modify things. Now, another thing that we did is we assumed a linear elastic material. This created a nice relationship between our stresses and our strains. Remember that we can find our stresses just by multiplying our strains by a matrix, basically. And we said if we have an isotropic material or an orthotropic material, all we're really doing is changing that matrix. That was it. Now, this actually was nice for us because this created a nice system where we can solve our problem using the following equation, where we have our stiffness multiplied by displacement is equal to basically our nodal forces. And again, everything was kind of independent of each other. I can calculate that stiffness first if I wanted to. I can calculate that force if I wanted to. It doesn't matter. I calculate both. I throw it into the equation. I'm good to go. Now, when we're dealing with a nonlinear analysis, things get a little bit more crazy. That equation that we had above, that we simplified, it doesn't simplify as much. First of all, we don't have a nice stress-strain relationship. And another thing too is when we're dealing with different materials, the stress-strain relationship is of course going to change. My stress-strain relationship for steel is going to be different than concrete, something like that. Another thing too is those loads that I'm placing on my structure, they're actually dependent on the deformation of the structure itself. One of the most low-key assumptions that we made in that small deformations was that when we're doing these integrals, remember, we're integrating over the element, but when we were doing those integrals, we were integrating over our undeformed or our reference domain. And again, if we're doing small deformations, that's perfectly valid. If I have a beam and all I do was this to the beam, just tilt it just a little bit, well, the reference domain and the deformed domain are going to be very similar, so that integral is not going to be too bad. But if I have a beam and I deform it like crazy, well, of course, there's going to be a big difference between that reference domain and our deformed domain. So we actually have to start taking that into account, something we didn't actually do before. So we're going to look at different types of nonlinearities. And the goal of this course, moving forward, is how can we basically account for these nonlinearities in our finite element analysis. Again, the theory is going to kind of take a back seat here. We're going to learn more about how to implement it, but we still need to be aware of what these types of nonlinearities are. The first one that we're going to kind of tackle today, for the most part, is a geometric nonlinearity. So question for you guys in the chat here, what do you guys think is a geometric nonlinearity? Do you guys know any? This is kind of a harder one for students to comprehend, but yep. P delta effects, of course. That's a geometric nonlinearity. Yep. I'm looking for a big one. You guys should all know this one, especially you civil engineers out there. No takers? Yes, exactly. Buckling. Buckling is a geometric nonlinearity. So that's one of the things we're going to have to account for. Another one is, of course, large deformation of the material. If we were to start deforming that material, we need to take into account the change in the material or the geometry. Couldn't say that word for some reason. But we have to take into account that geometry. For example, if I were to have a bar right here, just a nice easy bar, and I were to start pulling it, we know just by kind of intuition that it's going to look something like this. Now, that cross-section just changed. But in our equations before, we didn't take into account the fact that that cross-section is changing. We dealt with the initial position of the bar, the initial geometry, and we used that throughout our whole analysis. But if we're getting to the point where things are starting to change, we actually need to take that into account. All right, so that's kind of the first one. Excuse me, guys. The second one is material nonlinearity. So the first one, of course, is going to be plasticity. which basically means that at some point in the material, once I start stretching it, it's going to have plastic deformation, or basically irreversible deformation. If something is elastic, I can stretch it, and when I let go, it's going to return back to the original position. When something enters the plastic region, I stretch it so it's plastic now. When I let go, it's not going to return to the original position. It's going to have some residual strains. So that's one of the first one. Second one is going to be damage. And the best example I give with damage is concrete. And one of you guys mentioned the cracks in concrete. Once I crack concrete, it stays cracked. When I push it back, of course it'll make contact with itself again. But those bonds that I once had, they're not coming back. It's gone. So that's something we have to take into account. Now, up until this point, when we're dealing with the stress-strain curve, we assumed that things were nice and elastic. Now, if this was steel right here, again, this is probably pretty fine for most everyday scenarios. In typical everyday scenarios, we're not actually yielding our steel or anything like that. But it's something that we have to take into account, that if we had a catastrophic event or something crazy like an earthquake, our steel will probably yield. And our material behavior can't just be defined by this simple linear curve. It has to have that plastic portion after it yields. So this is going to be one of the things that we talk about next lecture. How do we incorporate that behavior into ABAQUS? Now, if we were to look at concrete in compression, we know that it's almost kind of a parabolic shape. Now, what makes concrete so much worse than steel? Well, actually, I'm going to give you guys a question. This will be a good question for you guys. So this is concrete in compression. And when we start talking about plasticity math, we're going to touch on it. We're not going to get too into details, but we're going to touch on it. What is the problem with concrete that steel doesn't have? My civil engineers out there. What's the major difference between steel and concrete besides just the parabolic shape in terms of behavior? What is something that's really going to bite us in the ass when we start looking at the math of concrete? Tension and compression. So steel behaves the same way in compression as it does in tension. Now, of course, in compression, it can buckle either globally or locally, and we're going to discuss that. But concrete has a different behavior in tension as it does in compression. And that's going to make the math kind of a real bitch, as you guys will see later. And the last one is a kinematic nonlinearity. Well, there's actually more types of nonlinearities, but these are the main ones. So kinematic nonlinearity, even though it sounds kind of crazy, it's contact. Very simple. If I had two objects coming together, we know that at some point they're going to hit each other and make that contact. Now, again, when we're dealing with a finite element program, if I don't specify contact, what's going to happen is the two shapes are just going to go right through each other. You guys can try it right now in ABAQUS. You guys know how to create a simple square. Just create two of them, push them together. They're just going to go right through each other. Nothing's going to happen. Now, the problem with this contact, and when we're dealing with nonlinearities and their complexity, this contact is actually one of the worst. Plasticity, as we can see for the materials, it's not too bad. Geometric nonlinearity, it's actually probably the easiest. But that contact, that's where things get crazy, because we have basically two surfaces of each object, and they have no stress. And then at one single time increment, as soon as they touch, the stresses go crazy. So that's basically going from 0 stress to 100 stress in 0.1 seconds. So it gets kind of crazy when we start dealing with that contact, especially if we start talking about impact. Now, of course, that time increment in which it makes the contact, that's going to play a big role. And we're going to talk a little bit more about that in lecture number 9 when we start talking about contact. Now, the question is when we start looking at that equation, what we're going to end up having is a series of nonlinear equations. The question is, how do we solve them? Let's say that I account for all my nonlinearities and I have my equations. The first thing we're going to look at is how do we solve it. In a linear system, our solution was nice and simple. We had k multiplied by u is equal to f. Nice linear system, we can solve it. However, we don't really have that when we're dealing with these nonlinear equations. So to solve these nonlinear equations, we typically employ the Newton-Raphson method, which is also called Newton's method. So in ABAQUS, if you guys were to look at the documentation, it says Newton's method, but what it's actually referring to is Newton-Raphson method. Now what happens is why is it called Newton-Raphson method? Well, basically Newton created a method and then Raphson generalized it. That's it. It's basically, no, not basically, it is the exact same method except one's just generalized. So it's the same method, hence Newton-Raphson method. Now, this method actually gets kind of complex. And the reason why is because when we're dealing with those nonlinear equations, we have many of them. We don't just have one equation, one unknown. We have many equations, and each equation has many unknowns. Now, if I were to actually scroll back really quick, I want to show you guys what exactly equations I'm talking about. It's this one down here. Basically, we are going to solve this equation for the unknown virtual displacements such that this equation is maintained. This equation here, you guys may not remember, but this is basically equilibrium. We're going to iterate through the possible displacements such that our equilibrium is satisfied. Now, if we're solving through the displacements, and again, we're having the nodal displacements, basically every degree of freedom in my system, that's one equation. And every degree of freedom in the system, that's one unknown in the equation. So if I have 4 degrees of freedom in my system, I have 4 nonlinear equations, and each one of those equations has 4 unknowns. So hopefully that makes sense to you guys. Now, getting into this equation, outside the scope of this course, we're not actually going to get into it. All we're trying to do by the end of this lecture is to show you guys if we have these nonlinear equations, how do we solve for them? Because we have to realize that in our finite element method, we have nonlinear equations. ABAQUS, ANSYS, whatever you guys pick, it solves for them. And we're going to show you guys what exactly ABAQUS and ANSYS does, which is, again, this Newton-Raphson method. So we're going to start off with the single variable case just to make things easy so you guys can see what exactly is going on with this method. And then we are going to apply it for our many equations with many unknowns. So if we have a continuous function f, we know that we can expand it using a Taylor series expansion, where basically f of xi plus 1 is equal to f of xi plus the partial derivative of f of x multiplied by the distance between them, etc. So this Taylor series, you guys seen it before, it's nothing too special. Now what we're going to start doing here is we're going to say, you know what, those higher order terms, they look like garbage, I don't want them, get them out of here. So the first thing we're going to do is neglect the higher order terms. So the highest order derivative in our equation is now just one derivative. We have d of f of x with respect to x, and that's it. We don't have any second derivatives. We don't have any third derivatives, just one nice derivative. And this allows us to simplify our equation into the following here. And this actually looks pretty nice, where we have f of x, where it's at I plus 1, is approximately equal to f of xi plus the derivative of f of xi with respect to x, and then multiplied by xi plus 1 minus xi, or basically delta x, the distance between these 2 points. Now, I'm going to be honest with you guys, when I look at math, I don't like it. Like, it looks scary. I don't know what that's saying. So in the next slide, we're going to provide some actual context. So if you guys can actually picture what's going on with this equation, don't worry, it'll make sense in the next slide. Now, what we're going to do is we're actually going to separate that xi plus 1 minus xi, or basically that delta x. So the change in distance between those 2 points we're going to find as delta x. And now just for fun, we're going to say that kt is actually the derivative of f of xi. So the derivative. Now, where does this appear? Well, it appears in the bottom of the equation right here. So this allows us to simplify our equation into the following, where we have f minus f of xi divided by kt is equal to delta x. Excuse me, guys. So what's basically happening is this. F, that big capital F, that's our desired value. That's what we want to achieve. For instance, if I were to load a beam and I applied 200 kilonewtons, that 200 kilonewtons, that's what I want to try and achieve. I want to keep loading this until I reach 200 kilonewtons. Now the displacement of the beam, that would be delta x. We keep increasing that displacement until we reach that 200 kilonewtons. And again, this will make more sense in the next slide. But what I'm also going to do with this equation is I'm going to rearrange it. So rather than having kt at the bottom, I'm going to move it kind of up to the top by just putting a -1. You guys are saying, Clayton, you're trying to simplify it. Why did you make it more complex? Well, this will actually make sense later. All right, so even though it looks like I made it a little bit ugly, I actually made it a little bit nicer, and this will be shown a little bit later. So now what we're going to do is we're going to examine the parameters of this equation that we just derived, but in the context of some meaning. So let's say that I have a curve right here. Let's say that this is a stress-strain curve, and our stress-strain function is defined by f of x. What's going to happen is that that big F there, that's the value we want. So again, if I'm loading this, I want to load it up to a certain value. I say I want to load it up to the value F. The question is, how do I get to that value F? Well, first of all, I pick an initial point of X. Initial point of X. So in this case, I put just xi there, nice and simple. What's nice for us as civil engineers or mechanical engineers is what is typically going to be our initial guess, xi. What do you guys think? What do you guys think is going to be our typical initial guess as structural engineers? Static displacement? You guys are overthinking it. It's going to be 0. Yep, Sabrina got it. It's going to be 0. The reason why is when we start our analysis of a beam, doesn't matter what we're doing, it always starts from rest. Therefore, we have 0 stress, 0 strain. So it's very easy then to start applying our load increments. Now, associated with this value xi is we have our initial value of the function. So at this very particular case, we can figure out what f of xi is, no problem at all. Now, kt, what was kt? Well, this is the slope of the tangent line. So what's going to happen is at this initial point here, it's going to have a tangent line. All right, nice and simple. How do we calculate that tangent line? Well, it's based upon where that point is and what our function is. So what we're going to do is we're going to extend that tangent line all the way up until it meets our value of f. From there, once it meets that value, we're going to draw a straight vertical line back down, and we're going to say that the distance between those two lines, that's going to be delta x. So after this increment at this new point, we have our f of x, sorry, we have basically what is a triangle here, a triangle. So we know that the height of the triangle is going to be our desired value, the one we want to get to, minus what we are initially at, that distance, delta y basically. We know the slope of this line. So since we know the slope of the line as well as the height, we can figure out what that delta x is going to be. Now what's nice is after we figure out what exactly that delta x is, we can say that this new point is x of I plus 1. Nice and simple, right? At least I'm hoping so. And at this value here at I plus 1, we have a new value of f of x, or a new value of stress. So I'm hoping you guys are starting to see what exactly has happened. We start off with an initial value, we perform an increment, and now we are one step closer to that desired value of f. That's basically all we're doing. Now, in an FEA context, f minus f of xi, that's going to be the difference between our applied forces and our internal forces in the FEA context. And delta x, this is typically going to be our displacement increment. It makes sense. So what happens is if we have a beam in our FEA model and we apply 200 kilonewtons on this beam, what we're basically going to do is we're going to increase that displacement until our forces balance. Basically is what's going on. Nice and simple. Now, if you guys are looking at this and saying, you know what, Clay, not nice and simple. You're so full of crap. It's not nice and simple. Well, let's look at an example and hopefully you guys can see what exactly is going on. So if we have a function, f of x is equal to the square root of x, and we want to find a value of x such that f of x is equal to 3, what do? So if you guys were to talk about this in, let's say, a civil engineering aspect, it's saying that let's say our stress strain function is the square root of x, and what we're basically saying is what value of displacement do I have to put in, or what value of strain, so that my stress is equal to 3. That's all we're trying to do here. And we're going to solve this through the Newton-Raphson method. So we know that our desired value of stress is going to be 3, right? That's what we're looking for. And this is typically our applied loads. We know what our applied loads are going to be. So the question is, how do we get to those applied loads? So if we look at our function information, we know that f of x is simply the square root of x. And we know that kt, which is the derivative of f with respect to x, is going to be 1 divided by 2 multiplied by the square root of x. Now, question for you guys in the chat, what is going to be our value of x that gives us 3? You guys in the chat. What's our value of x that's going to return us with the value of 3? What do you guys think? What is the exact solution here that I'm looking for? Just before we get into these iterations. 9? Yeah, exactly. It's 9. If I were to substitute x is equal to 9 into our function, square root of 9, 3. So that's what we're looking for, 9. So let's see what this Newton-Raphson method does to get us to a value of 9. So what I'm going to do is I'm going to make a chart of all the parameters. Now the first thing that we're going to do is we're going to have that initial guess. And what I'm going to do is I'm going to say my initial guess right here, it's going to be 1. Okay, 1. So on our chart here, I now have a value of 1, and again, this is just a guess. You guys can guess whatever you guys want to start. It will impact the speed it takes, but not really a lot. So I'm just going to say it's 1. Now what I'm going to do in my next column is I'm going to figure out what the value of my function is at that initial guess. So if I were to substitute x is equal to 1 into my function, we get the square root of 1, or basically we just get 1. So what I'm going to do on my graph here is I'm going to say, all right, at the value x equal to 1, my function returns us a value of 1. So if this was, I don't want to use stress or strain because strains are usually small values, stresses are large values. I'm going to use load displacement, okay? So what this is saying is that currently I applied 1 millimeter of displacement and my load is 1. But I don't want a load of 1. I want a load of 3. So again, what I'm trying to do is I'm trying to find the displacement to give me my desired load. So right now, it's not good. I have a displacement of 1, but my load is only equal to 1. I want to try and get to that load of 3. So what I'm going to do is I'm going to figure out what the slope of the tangent line is at this initial guess. How do we do that? Well, we have a nice formula here. Remember, it's simply the derivative. So kt is equal to 1 divided by 2 multiplied by the square root of x. Now x there, that's our initial guess, which is going to be 1. So basically kt is going to be 1 divided by 2 multiplied by the square root of 1, which is 1, or basically kt is going to simply be 1/2. Now what this means in the graph is at that point there, we just drew a tangent line. A nice, simple tangent line. And we extend this tangent line up until it hits our desired value of 3. All right, so from here, we're going to find out what that increment is. That distance between our initial point and the point where our tangent line hits our desired value. We have a nice formula for that we derived, where delta x is equal to kt times, or to the negative 1, multiplied by f minus f of xi. Well, we know our kt is 0.5, so we're going to go 0.5 to the negative 1. Our desired value of f is 3. Remember, we want that load of 3. And our current value of load is simply 1. So we're going to go 3 minus 1, which gives us 4. So this delta x right there, we know it's going to be 4. What does this mean on the graph? Well, this means that we've moved now a distance of 4. So our new displacement, or our new initial guess, it's going to be 5. So we went from 1 millimeter of displacement, now we're at 5 millimeters of displacement. Now my question for you guys is, at this 5 millimeters of displacement, have we achieved our load of 3? What do you guys think? Have we achieved our load of 3 at 5 millimeters of displacement? No, exactly, we have not. So what do? We throw in another iteration. What's our new initial guess? Well, it's going to be our final guess from our last iteration. So now we know that we are at a displacement of 5 millimeters. We're going to say, all right, well, at this point, I need to figure out what the value of my function is. Well, it's going to be 2.24. So as we can see, again, we want to get to a load of 3. Our initial guess was 1, which is kind of far off. But now we're at 2.24, which is a lot closer to 3. Where's this 2.24 on the graph? Well, that's going to be right here. Now what we're going to do is we're going to recalculate that tangent. So again, 1 divided by 2 square root of x. But now instead of x is equal to 1, we have x is equal to 5. So kt is going to be 1 divided by 2 times the square root of 5, which is around 0.22. From here, we go back to our graph, and we're going to draw that tangent line, just like we did before, and we're going to get something like this. From here, now that we know what kt is, as well as f of x, we can figure out what our new delta x is, and it's 3.42. What does this mean on a graph? Well, it means that we now moved an additional distance of 3.42. So our total distance now is 8.42. So on a graph here, we have 8.42. So now what we're saying is that we've displaced 8.42 millimeters. And my question for you guys, at 8.42 millimeters, do we have our desired stress of 3? Or a desired load of 3? What do you guys think? Are we good to go at 8.42? So good question. We're getting close. And this is going to be one of the things we start to discuss later. How close is close enough, sort of thing. So we're going to discuss what exactly that will be later, and we're going to discuss how exactly ABAQUS deems it. So let's just say, you know what? Not close enough. I want to do one more iteration. So I'm going to take that 8.42, and I'm going to make it my new starting point yet again. I'm going to evaluate f of x as well as kt when x is equal to 8.42, and I get the following. Now at this point, after I've done this third iteration, I get my f of xi is equal to 8.99. So that's way at the end here, and this is basically close enough. At this point, we did 3 iterations, and we said to get a load of 3 from our Newton-Raphson method, we need to apply a displacement of 8.99 millimeters, which is essentially 9. Of course, as we do more iterations, it's going to get closer and closer and closer, but 8.99, when we know the answer is 9, that's going to be pretty good. So the Newton-Raphson method in single variable, how are you guys feeling? Is it pretty good? Not too bad? What do you guys think? You guys don't want to comment? Is it that bad? Great. All right, I heard a great. Perfect. Now we're going to discuss multivariable. Again, what happens with these nonlinear equations is we're solving for those nodal displacements. So depending on, oh, sorry. Oh, got some stuck in my throat. So depending on how many nodal displacements we have in our system, that's how many equations we're going to have. And again, how many nodal displacements we have in our system, that's how many variables we have in each equation. So we're not just looking for one equation with one unknown, we have multiple nonlinear equations with multiple unknowns. So unfortunately, most scenarios in FEA, they involve many equations with many unknowns. So buckle up, guys. Things are about to get a little bit messy. So what we're going to do for this proof, it's going to be almost identical to the one before, is we are going to, again, perform our Taylor series expansion for each equation. So we're going to do it once for F1, we're going to do it again for F2, all the way down to Fn. So if I were to focus on F1, I get the following expansion, neglecting higher order terms. So I stopped after that first derivative. Now it looks like complete garbage. I know I'm probably scaring a lot of you guys right now, but don't worry, it's not too bad. If we look, it's the same thing as before. Before, our first part of the equation was our function at our initial guess. That's the exact same thing here. And then the second part of our equation was basically the derivatives of our function multiplied by that delta x. Well, that's exactly what appears here. The only difference, and the reason why I now have 3 terms, well, it's actually a lot more than 3 terms, but the reason why I have more than just 1 term is because when I'm taking that derivative of our function, now I have to take it with respect to each of those unknown variables. So if I look at that first component there, it's the derivative of f1 with respect to x1. Our second component, the derivative of f1, with respect to x2. And this goes on for all of our unknown variables until we get the derivative of f1 with respect to xn. And what we're going to do is, this is just for one equation. We have to do this for f2, f3, all the way on until we reach our total number of equations. Now, it looks like it's going to be really bad, but what's nice is we can actually write this in matrix form. Again, matrix form also looks pretty bad, but it's not as bad. The first part here, this is our function at that initial value, just like we had before. The second part here, this is the derivatives, which I separated into its own specific matrix, and then I multiplied this by a vector of basically those delta x's. So even though it looks really bad, it's not too bad. Now I got a fun question for you guys. All right, fun question. I don't expect you guys to know this. Basically, I just need a water break, so I'm trying to stall a little bit. That matrix of derivatives right here. So that first part in that purple box. Do you guys know what that matrix is called? What do you guys think? You guys have any idea what this matrix right here is called? The gradient? Close. It's actually called the Jacobian. That's one of the beautiful things about finite element is when I first did the Jacobian, back when we did it in our isoparametric elements, I thought that that was unique to that very specific scenario. What happens is the Jacobian is actually a mathematical term, where we're basically taking our function and we're taking the derivatives with respect to each of the parameters. So that's called a Jacobian. Little fun fact, don't worry too much about it. So we're left with this equation. But just like before, we're going to modify it. Before we said we simplified it, well, we're dealing with a big ugly matrix. There's not really much to simplify. So the first thing I'm going to do is I'm going to take that initial value, f1 of xi, f2 of xi, etc., and I'm simply just going to move it over to the other side. That's all I did. From the previous slide to this slide, all I did was move that over to the other side. And the reason why is I can now write this in a more simple format where I have k multiplied by delta x is equal to our f, which again, those will be our desired values, minus f of xi. I'm sorry, I'm not sure if you guys can hear that. As I told you guys a little bit before, the apartment flooded, but construction is beginning now, so you guys might get a little bit of interference, so I apologize for that. So what we're going to do is we're going to move that kt now to the other side, and we get the following equation. And if we look at this equation, it is the exact same as our equation that we did for single variable. The only difference that we have now is instead of dealing with just single values for each parameter, we now have a matrix and vectors. That's the only difference. So remember before when I moved that kt as an inverse, so I said kt to the -1, and you guys are thinking, this guy's nuts, this guy's Looney Tunes. Well, this is why. It's because it allows it to keep it consistent no matter how many variables that we have. Now, if this looks crazy, don't worry, we're going to solve an example and hopefully it'll make a little bit more sense. But as we mentioned, there's other things that we have to consider now. Convergence checks. Before it was very easy in our example because we knew that our final value was 9. So all we did is we kept looking at how close we got to 9. We started off at 1. We said that's not very close. Or no, we knew our final value. Of x was 9. We started off at 1, not very close. We went to 5. We said closer. We went to like 8.4. We said, okay, now it's getting close, sort of thing. How do we do that in multivariable? Because now we don't just have one value of x that we're slowly putting up. We're dealing with all the nodal displacements. It's not just one value, it's multiple values. So in order to do this, we actually look at the norm of vectors. So that delta x that we get, that's going to be a vector. We're going to look at the norm of that vector. And of course, we want that norm to start shrinking, basically. So for force and moment convergence, what we do is we say it's achieved when the norm of the vector f of xi minus f divided by the norm of vector f is less than the specified tolerance. What does this mean in mathematical form? Well, basically this. We have f of xi, which is just a vector of all of our functions at our initial value, minus f, which is a vector of our desired values, and we just take the norm of it. On the bottom there, we have our vector f, and again, we're just taking the norm of it. And what we're going to do is we're going to say that convergence is achieved for this criteria when this value is less than our specified tolerance. Now, if you guys go into ABAQUS, you guys can actually look at the specified tolerance, and you guys can actually play with it. Now, it's something that ABAQUS does not recommend. If you go into that menu where the tolerances are, ABAQUS basically says, hey, if you start messing things up, it's not our fault, it's your fault. So it gives you kind of a warning that says you're playing with things you shouldn't be playing with. So for force and moment convergence, ABAQUS usually uses a value of 0.5%. If that is converged within 0.5%, things are usually deemed pretty good. But we also have displacement convergence. And this is going to be important, as you guys are going to see in your guys' assignment. So what happens is sometimes the values converge, but it's not on the right value. This is why we have two different values of convergence. So it says force convergence here, but this is displacement convergence. Don't listen to this. Displacement convergence is achieved when the norm of our vector delta u, or delta x, divided by the norm of vector xi is less than a different specified tolerance, aka this right here, where delta x, that's a vector, we take the norm, xi, that's going to be a vector, we take the norm, and we make sure that that is less than the tolerance. Now for ABAQUS, this is typically 1%. 1%. Now what happens, and the reason why we need both, is sometimes, again, we will start converging upon a value, but it'll be completely wrong. So what happens is this displacement convergence will converge, and ABAQUS will go, oh, things are great. But then when it checks the relationship between that value we converged upon to our desired value, there could be a huge difference. So this is why we have to make sure that both of these are actually maintained. What typically happens is if this displacement convergence is converged upon the wrong answer, then we modify that initial guess and kind of play with it from there. And this will be something, again, you guys will see on your assignment. So let's look at an example where we have these multivariables. So if we have two functions, we have f1, which is 20x1 to the fourth, x2, plus 3x2 cubed, and we have a second function f2, which is 20x1 squared times x2 cubed. The question is, how can we solve for x1 and x2 such that our function now returns us with 20 and 1? If you guys really want to think of this in terms of, let's say, finite element, basically, I have two different nodes. At node 1, I apply a load of 20, and at node 2, I apply a load of 1. How can I figure out what my displacement is going to be to achieve those two loads? So hopefully that makes sense in how we're actually trying to talk about it. So one of the things that we know that we're going to need is that tangential stiffness matrix, that KT. And we know that this is simply going to be a table of partial derivatives. If we look at the first row there, it's always going to be the derivative of f1. The only difference is we're changing we want it with respect to. So first column there, or sorry, the first entry, we have the derivative of f1 with respect to x1. The second entry, the derivative of f1, now with respect to x2. If we look at the bottom row, it's this exact same thing, but instead of f1, we have f2. And this is nice because f1 and f2, we know what exactly those are. Therefore, we can take them, take their derivatives, and we get the following for KT. Now, things are going to get a little bit messy because, of course, our table just got a lot bigger. Because instead of solving for one single variable and finding the function at that variable, we now have two variables. Therefore, we have to take the function value at two different variables, and then we get two different delta x's, etc., etc. So what I'm going to do is I'm going to say that x1 and x2, they're equal to 1. All right, they're going to be equal to 1. Now, my question for you guys in the chat, why are they equal to 1? Why are those two values equal to 1? What do you guys think? Why are those two values equal to 1? No one wants to be brave? You guys are reading into it too much. The answer is they don't have to be equal to 1. They can be whatever you guys pick them to be. I just picked 1. So when you guys are doing your assignment, don't try and look for that initial value. Just pick a value and see if it works. If it doesn't work, then you can modify it and try again, sort of thing. You guys are reading way too much into this. So what we're going to do is we're going to do sample calculations for that first iteration. So hopefully this makes sense to you guys. So if we look at our next column, we need our function value at xi. Well, we know that xi is simply going to be the point 1, 1. So f1 at 1, 1, well, we know it's going to be equal to 23. So we have 23 in that column. Moving on to the next column, we now want f2 at xi. So we're going to find f2 at the value 1, 1, and we figure out that that's going to be 20. So I can throw 20 into there, no problem at all. Now, in order to get delta x1 and delta x2, I need to find what that tangential stiffness matrix is, that matrix of the derivatives. Well, this is easy because I have a nice formula above. all I have to do is substitute the values of our initial guess. So of course our initial guess is x1 is equal to 1, x2 is equal to 1. I just substitute it in the formula above, and I get the following matrix. Now with that matrix, I can come down and say I can figure out what delta x is, as it's simply kt inverse multiplied by big F minus small f, or f of xi. Well, all I have to do is substitute values. I throw in my kt inverse. I know that f, the value I'm trying to achieve, is 20, 1, and I know that my current value is 23, 20. And if I throw all this into Mathematica, MATLAB, whatever you guys want, I get the following thing right here, where I got 0.102 in my first entry and negative 0.385 as my second entry. So my question for you guys, if I wanted delta x1, the next column, basically, what is my value of delta x1? What's going to be my value of delta x1? What do you guys think? 0.102? Exactly. Because we just solved for what delta x is, and delta x is simply going to be a vector. Delta x1, delta x2, and if we had a certain scenario, delta x3, etc., etc. So if we look right here, delta x, well, the first entry is 102. Delta x2, well, that's going to be the second entry, which is negative 0.385. So in our columns over here, we can input them. And then from there, we can find our error in our force, which is 96%. And we can find the error in our displacement increment, which is 28%. So from here, we look at this and say, you know what? We're going to need a new iteration. Let's modify our initial guess and go from there. How did I get this initial guess? Well, we had our initial guess as 1. We said that our delta x1 is 0.102. So 1 plus 0.102, that gives us 1.102. If I were to look at x2, I start off at 1. My delta x is negative 0.385. 1 plus negative 0.385, that gives us our 0.615. From there, I just carry the iterations out again. And as we can see, we start to get closer. Now our error in our force is just under 24%, and the error in the displacement is 19.7%. Not very good. Do another iteration, and in this iteration, I can see that I'm starting to get my errors under 10%. So it's starting to now converge. I can keep going on to the point where I have my initial guesses that result in pretty good errors. 0.1% for force and 0.04% for displacement. Now this actually only took 6 iterations, so I'm only missing like 2 or 3 columns in there. So it converges very, very fast. And what's nice is we can see right here that this is our value of f. So we wanted 20, 1. And if we look under these values of our displacement, we now get 19.98 and 1.001. So it's basically 20, 1. Converges nice and fast. So that is the Newton-Raphson method for multivariables. How's that sitting with you guys? Pretty good? Not too bad? Hopefully not too bad. You guys are shy today. Don't worry. By the final lecture, I'll make sure that no one's shy anymore. We're all big, one happy family here. There's no need to be shy. So let's discuss some other methods, because as we're going to see in ABAQUS, it's not always just Newton's method. There are other methods. And the reason why we have these other methods is to improve stability and reduce computation time. That reducing computation time is kind of a common theme here. You guys have seen it so much. So the first one is the modified Newton-Raphson method. All right, the modified Newton-Raphson method. All this method does is it says that KT that we recalculated at every increment, well, we're only going to recalculate it now at select increments. Or we're just going to keep it the same for the entire analysis. Now, this requires additional computations to converge, but overall it actually reduces the computation cost, because the cost of those additional computations is less than the cost of actually recalculating what that KT is. So that's going to be the modified Newton-Raphson method. It's on your assignment, but we're going to do an example. As you guys are going to see, it's the exact same thing as the Newton-Raphson method, the original, except that KT, we're not recalculating it every time. We calculate it once and we kind of just leave it. Or we calculate it every fifth increment, something like that. Now, the second one, and this is the one you guys are going to see in ABAQUS, is called the secant method, or the quasi-Newton method. Now, what we do in this method is we actually approximate that KT after the first iteration. All right, after that first iteration. And we do this by figuring out the value of our function as well as our two initial guesses from the previous iteration. So we have to calculate that KT once to get to the second iteration, but after that, from the second iteration on, we use kind of the formula below, and there's variants of this formula. So this isn't the only one, but basically we approximate this. Now, what's nice about approximating this is that we actually don't need to calculate any more derivatives. As we're going to see, a lot of the examples that we did, the derivatives, they're not so bad. But in a true nonlinear analysis where everything is nonlinear, those derivatives suck. So this provides a really nice method in that we actually don't need to calculate those derivatives anymore. This provides a good convergence rate while reducing computational costs. So convergence rate is something that is still being researched very heavily today. But if you go to a lot of articles, they usually prefer the secant method. Now, ABAQUS by default in a linear analysis is going to do the Newton-Raphson method by default. But if you guys want to, you guys can pick the secant method. And later on today, we're going to go into ABAQUS and show you guys just exactly how we can pick these different methods. But before we do that, we're going to do a quick example. And this is going to be the exact same example that we did before, but instead of using the Newton-Raphson method, we are now going to use the modified Newton-Raphson method. All right, the modified Newton-Raphson method. So just like before, I'm going to say my initial guess is 1. On our chart, that's over here. I can evaluate my function at 1, which is going to be 1. So on my chart, that's going to be right there. And this just goes to show how horribly off my scale is. So I apologize for that, guys, but hopefully it doesn't bother you guys too much. And just like before, we're going to proceed. We're going to calculate KT, which is 0.5. So on our graph, we have our nice tangent line slope, and we're able to find delta x, which is 4. So up until this point, absolutely nothing has changed. Our new guess right now, xi plus 1 is going to be 5. So we carry that downwards into our next initial guess. So now that we have xi is equal to 5, well, I can figure out the value of our function at 5. It's just the square root of 5. So 2.24. And now my question for you guys is, what is going to be KT? Now that we have xi is equal to 5, what is going to be the value of KT? Question for the chat. I have what my initial guess is. What is going to be the value of KT? 0.5. You guys are on the money. Exactly, 0.5. The modified Newton-Raphson method, we don't modify KT unless it's at very specific iterations. So in this case, we're not going to modify it at all. So instead of recalculating KT, we're just going to keep it as 0.5. So if we were to look at our tangent line, it's going to be the exact same as before. This will give us a new xi plus 1 as 6.52. So what do we do? Well, we do another iteration. As we can see, we're getting closer to the value, but our convergence rate is now a lot slower. So remember that in the previous example, by this third iteration, we were at 8.99, but now we're at 7.41. Well, how about another iteration? Well, even after this iteration, we're at 7.97. We're still almost 1 off from our desired value. So this method, it works. As we can see, eventually we will get there, but it provides a much slower convergence rate. All right, so that is the Newton-Raphson and the modified Newton-Raphson method. How are you guys feeling about this method? Is it making sense to you guys? Is it a bit complex? What do you guys think? That's the end of the PowerPoint too, by the way. What do you guys think? I'm curious to know your guys' thoughts. No one's brave enough to tell me their thoughts? It's fine? All right, and I got a smiley face, so thank you. I appreciate that. It must be good. So what we're going to do is we're going to take a break. I know I kind of went over my time a bit, but when we get back, we are going to jump into Mathematica, and we are going to solve a nonlinear example. So what we're going to do is we're going to solve for the displacement of a bar element, just like we did before, but now we're going to say that our stress-strain relationship is now nonlinear. So we're going to come back, we're going to solve this problem, and then we're going to have some fun in ABAQUS. So in ABAQUS today, what we're going to do is we're going to look at how to create some unique shapes, so some unique parts or 3D parts as well. And then we're going to start talking about kind of the Newton-Raphson method in ABAQUS, that idea of iterations, stuff like that. So that's going to be what we're going to do moving forward. So again, we're going to take, we'll come back at 9:30. So we'll take a nice almost 10-minute break, rejoin each other at 9:30 and continue the fun. So if you have questions, throw them out in chat, and when I get back, I'll be happy to answer them. I just got to go refill my water, of course. All right, guys, I will see you guys at 9:30. All right, guys, I'm back. Don't worry, we're not going to start until 9:30. So if you guys are still, grabbing your popcorn, taking a break, by all means, enjoy your time. I just wanted to come let you guys know I'm back in case you guys have any questions. Or I have a question for you guys. How's the course been so far? You guys learning something, or has it been more or less trivial for you guys? I'm curious. Everyone's experience with finite element is so different, so I really enjoy the feedback that you guys give. Pretty good. Good. Great. Okay, good. As long as you guys are learning something. I don't like classes that you take and you're like, how will this ever impact anything in my life? But I was glad to see that you guys are kind of seeing it or appreciating it. I don't know the word to say. All right, so I'm just gonna save our file really quick. And yes, this not this one. I prepared a nicer version, and I'll upload that into E-class so you guys can see. We'll call it material nonlinearity. I'll just call it class, something like that. So I'm just gonna type in my go-to clear really quick before we begin, so that every time we rerun it, we'll have nice fresh variables and no errors will hopefully occur. You never really know. Yeah. Now that you guys are more awake, I'm gonna ask you guys again. How are you guys doing? Are you guys doing okay? How's this semester been? Forget about this class for a second. How's life been? Life been good? Besides the pandemic, I guess. I guess it's kind of a loaded question right now. Good? Busy? Well, as long as it's good. You guys catch that new Pokemon announcement, or am I just a nerd and you guys are laughing at me? Anyone here excited for the new Pokemon? No? Maybe? No, I'm definitely the nerd. That's okay. Nothing wrong with that. I might as well just put material nonlinearity example. All right. Well, 9:31. Time to get started on this example. So, as I said, this example is something that we basically have done before. The only difference now is we're going to say that our stress-strain relationship is nonlinear. Before, when we had one of these bar elements, we said that we had a nice stress-strain relationship where our stress is simply equal to our Young's modulus multiplied by our strain, and that basically made everything nice and simple. In this case, well, we're given that our stress is a function of strain, but it's not a linear function. So how can we solve this problem using the Rayleigh-Ritz method? And as we're going to see, how can we actually obtain the exact solution for this? So what I'm going to do to start is I'm just going to create my parameters as I normally would. And as we can see in this beam, we basically have three parameters related to the beam itself. The first one is the length of the beam, which we said is 1. It's kind of just right here. We also said that the beam has a cross-sectional area of 1. And then finally, the load on the beam, P, is equal to x squared. So I'm just going to put x1 squared. So do you guys have any problem where I'm getting these parameters from? I basically just stole them right from the question sheet. Nothing too crazy yet. Hopefully you guys understand. If you guys have questions, just let me know in the chat and we can slow down and discuss. So in addition to our parameters, related to the beam, we're also going to have some Newton-Raphson parameters. Newton-Raphson parameters. And we're going to get more into what these are going to be a little bit later on in the analysis. So for now, I'm just going to leave it blank, but I'm going to keep it open so that later on we can come in and say, all right, I'm going to need these specific parameters. So we're going to just ignore that for now, and we're going to move on to the next one, which is going to be our stress-strain relationship. So again, before, our stress-strain relationship, nice and linear, allowed for all of our calculations to become nice and simple. Well, in this case, it's not so much. So we know that sigma, or stress, is equal to 10 times epsilon plus 100 times epsilon cubed. So what I'm going to do is I'm going to say that my stress is equal to 10 multiplied by epsilon. But when I'm dealing with a partial differential equation and I'm solving for displacement, I want everything in terms of displacement. And this will make more sense the next step. But what I'm saying to you guys right now is instead of having epsilon, I want displacement. So what is the relationship between epsilon, our uniaxial strain, and our displacement? What do you guys think? Question for you guys. What is the relationship between strain and displacement? Exactly, it's simply the derivative. So instead of putting our strain E here, what I'm going to do is I'm going to put U prime of x1. And again, if you guys are unsure why I'm doing this, just wait until the next step. It'll become very, very clear. So this is going to be 10 times epsilon, so 10 multiplied by U prime of x1. Now we need 100,000, so 100,000 times U prime of x1. And now this one is to the exponent 3. So all I did here was I took our stress-strain relationship, our nonlinear stress-strain relationship, and I just defined it in our equation above. Now again, a lot of you guys are probably saying, Clayton, why did you do it in terms of displacement rather than strain? Well, this is because we are actually going to determine our exact solution. Now in our exact solution, we solve our differential equation for the displacement. We're not solving it for the strains, we're solving it for the displacement. Therefore, our differential equation needs to be in terms of that displacement. So the first thing I like to do is I'm going to find what our differential equation is. And over here on the right, we have our bars under uniaxial load. All right, so this is something that comes directly from the notes as an intermediate step. We had this in the notes, but what we did is we said, oh, well, sigma is equal to Young's modulus times epsilon. So we basically have EA, which we took out, and then we have the derivative of epsilon. We kind of went from there and we simplified it for the linear case. But now we're going to go back to this formula right here and say, well, this is kind of different now. So we're going to take the derivative of sigma multiplied by A plus P, and that's going to be equal to 0. So the derivative function is, again, just that D function. And inside we have our stress multiplied by our area. So I'm going to have our stress, which we defined as S above. I'm going to multiply that by our area. Now we're taking the derivative of stress multiplied by area with respect to x1. So I'm just going to put in my x1 over there. And then to end the equation, we have that plus p. So I'm just simply going to go plus p. So hopefully now it makes more sense to you guys why exactly we are using u1 instead of epsilon. Because we're taking the derivative with respect to x1. And then when we solve our differential equation above, what did I do there? When we solve our differential equation below, whoa, I don't know why it does that. Do you guys know why it does that? All right, go down. Okay, maybe it's working now. Press enter and then the thing popped up. Spooky. All right, so we're going to solve this differential equation, and we're going to do it the exact same way we did before. So we're going to use our dsolve function. And we basically have two different sides we need to input. We need to input our differential equation and our boundary condition, and then we need to specify what equation we're trying to solve for and what is the parameter. So we're going to have 3 total inputs. The middle one is what is the equation we're trying to solve for? Well, we know that we're trying to solve for our displacement u as a function of x1. What is the variable? Well, we know it's simply going to be x1. So in this first part here, this is where I enter my differential equation. So I say that this differential equation above, well, we know it's going to be equal to 0. So now a little test for you guys to see how good your long-term memory is. If I were to run this, am I good to go? What do you guys think? If I were to run this, am I good to go? I'm solving my differential equation, which is equal to 0. I'm solving it for u of x1, and the variable is going to be x1. So if I were to press Shift-Enter, am I good to go? You guys are on your game. Boundary conditions. Exactly. So if we were to do this, it would still solve it, but we're going to have two c constants. How do we solve those c constants? Well, we implement the boundary conditions. So if this is my beam right here, what are going to be my two boundary conditions? What do you guys think? Remember, I'm solving everything in terms of displacement. So what are going to be my two boundary conditions for this beam? Fixed ends? Exactly. So with a fixed end, we know that the displacement is 0. So at the left-hand side, our x1 is equal to 0. We know the displacement has to be 0. So we're going to say that u is 0. That has to be equal to 0. We also know that u at L, so on the right-hand side, it's also fixed. So this also has to be equal to 0. So now my question for you guys, is this good to go? Is this good to go? Are you guys happy? You guys thinking, you know what, Clayton, this is great. I like this. P, good one. So in our differential equation, we forgot P. So I'm going to add my plus P over here. So now that our differential equation matches exactly what's over here. Good pickup. How about now? So technically, it is good to go. We have everything we need to find. The problem now isn't us. The problem now is Mathematica. If we try to solve this, it's basically going to take forever and then basically quit with an error. And the reason why is the same reason that we had when we were doing those integration of our elements. When the integration starts to get complex and these things start to get complex, we can't just use our integrate function or our desolve function. What we have to do is we have to add an n at the beginning, which basically uses numerical methods to try and solve for these. Otherwise, it tries to find an exact solution, and then it gets really messy and it can't really do it. So when we're dealing with these nonlinear things, and things are actually quite complex, we actually should add an n before this. It's exactly the same in the elements, where instead of using integrate, we had to use n integrate. Hopefully that makes sense to you guys. But if I were to run this now, it should be good to go. We get our function. So even though it doesn't look like we have our function, this is good. This is actually our function. So what I'm going to do is I'm going to store this function now as u exact. So u exact is going to be equal to u of x1, specifically when solution of 1. Now what I can do, and just to show you guys that this is legitimate, I can plot u exact over the beam length. So I'm going to go from x1 is equal to 0 all the way until L. So this is our displacement function in the beam right here. Hopefully that makes sense to you guys. So even though it doesn't look like we have obtained it, we actually have. So that's the exact solution. Now let's move on to our approximation. So what I'm going to do is I'm going to come down here and I'm going to put RR approximation. So Rayleigh-Ritz approximation. So let's see how well you guys remember how to do a Rayleigh-Ritz approximation. So my first question for you guys is, the first step in any approximation, what do we need to define? What is one of the things that we always have to define when we're dealing with these approximations? Exactly, we need to define our displacement function. So what I'm going to do as a first step, I'm going to call it my approximation function. Now, if we look at the question here, it says, assume that the displacement function is a second degree polynomial. So we're already given what we should do. So what I'm going to do is I'm going to go u approx is going to be equal to a naught plus a1 times x1 plus a2 times x1 squared. Is that a second degree polynomial? What do you guys think in the chat? Is this a second degree polynomial? Am I good to go? Or am I going crazy? I got a yes. I'm not going crazy. You guys are correct. This is a second degree polynomial. And again, the goal of the Rayleigh-Ritz method is to solve for these unknown a coefficients. So for a second degree polynomial, I have 3 unknown a coefficients. Now, what is the first thing I can do to help solve for some of those a coefficients? What do you guys think? What is the... Oh, you guys are completely on your game. You guys must have had a good teacher. You guys are probably thinking of your other teachers, not me, but yes, exactly. We were going to implement our essential boundary conditions. So I'm going to go essential boundary conditions. So we know that we actually have 2. So what I'm going to say is we have a boundary condition 1, which is equal to our approximate solution. And this specifically occurs when x1 is equal to 0. We know that at x1 is equal to 0, we have that fixed end condition. So all I did was I say our boundary condition 1 basically occurs at our approximate solution when x1 is equal to 0. Now what I'm going to do is I'm going to copy this because it's going to be the exact same below. And we know that boundary condition 2 is the exact same where we have that fixed end, but this occurs at x1 is equal to L. So those are going to be the locations of our 2 boundary conditions. So what I'm going to do is I'm going to solve for A1 and A2, because if I have 2 boundary conditions, I can solve for 2 coefficients, and I'm going to use these 2 equations to solve for it. So I'm going to use my simple solve command, which basically takes in 2 inputs. The first one is what are our equations and what are they equal to? And then on the other side is what are we trying to solve for? So we already said that we're going to solve for A0 and A1. Again, we have 2 equations. We can do 2 unknowns. And we know that boundary condition 1, well, this has to be equal to 0. Because boundary condition 1 is the displacement at x1 is equal to 0. Now, we know that the displacement at x1 is equal to 0 is 0. So boundary condition 1 is equal to 0. Now, the second one, boundary condition 2, also going to be equal to 0. And the same reason. Boundary condition 2 is the displacement at x1 is equal to L. Well, we know that since it's fixed, it's going to be equal to 0. So this is going to be our solve command. So what we can do here is this will actually solve for A0 and A1, and we're just going to store them after we do that. So we're going to say that A0 and A1 are going to be equal to A0 and A1, specifically when solution 1 at 1. So if I were to run this, what I get is that A0 is equal to 0, and A1 is equal to negative A2. All right, negative A2. So what I'm going to do is I'm actually just going to suppress this really quick, and I'm going to go into our approximation solution. We can see that our only unknown now is simply A2. All right, it's simply going to be A2. Now my question for you guys is, now that we've done these essential boundary conditions, so we figure out all the A coefficients that we can with those boundary conditions, how do we solve for A2? Or the other unknown boundary conditions. How do we solve for those ones? Or the other unknown A coefficients? How do we solve for A2? Using the Rayleigh-Ritz method. What is the goal of the Oh, you guys are on your game. Minimize that potential energy. Exactly. So if we come over to the side here, I put in some little tidbits of the Rayleigh-Ritz method. We want to minimize the potential energy. So this little uppercase, or I guess it'd be capitalized pi, this is our potential energy, and it's simply going to be equal to the integral of our strain energy density minus the work done on the system. So what we're going to do is we're going to get this equation, and then we're going to try and minimize it. But if we look here, we have 2 components. We're going to look at each component. Again, this first one here, this is the total internal strain energy. So what I'm going to do is I'm going to put total internal strain energy. So this is going to be the first component that we want. So if we were to look here, it's actually rather simple. We're integrating over the beam this u bar of x. Now this u bar is the strain energy density. All right, so this can be the strain energy density, and the question is, how do we get that? Well, before it was nice and easy because we had a linear elastic material, but now it gets a little bit more complicated. Hold on, I got a question. Why don't we solve it with more boundary conditions? So what other boundary conditions are you suggesting we do. It's a good question. If we have more boundary conditions, we should utilize them. So one of the things here is this is a bar element. So the only degree of freedom is axial. It doesn't rotate. Does that make sense? All right, perfect. As long as things are making sense in the end, yes. So if this was a beam, then yes, we would definitely throw in those rotation ones. But since this is a bar, we're only concerned with the axial direction. So that internal strain energy, the first thing we have to find is this strain energy density. So the strain energy density, which we'll call SID, why not? We know it's going to be the integral, so we're going to integrate of our stress. Now we're integrating our stress over our strain. So over here we're going to have our strain, which is going to be E from 0 to E. Are you guys confused yet? This basically integrates our strain over an unknown, this integrates our stress over a distance of E, or strain. Now, if we go back to our previous stress formula, we had it in terms of displacement. We didn't have it in terms of strain. So what I'm going to do is I'm going to copy this stress-strain relationship we had before. I'm going to paste it back in here, but I'm going to rewrite it now in terms of strain. So rather than in terms of displacement, I'm going to replace it now with E. So it's in terms of strain. So that way when I integrate my stress function with respect to strain, because remember, we're integrating now with respect to strain, while our function is going to be a function of strain, nice and easy. So if I were to run this now, as we can see, we now have our strain energy density. And this isn't where we finish off. Remember, this is our strain energy density, but what we actually want is our total strain energy. So now that I have our total strain, our strain energy density, this is the most confusing part, I promise. Now that I have our strain energy density, I'm going to take our strains and I'm going to convert them back into displacements. All right, I'm going to convert them back into displacements. So I'm going to say that our strain E is simply going to be the derivative of our approximation function with respect to x1. So every time we have an E in this equation down below, it's now going to replace it with the derivative of our approximation with respect to x1. And the reason why we're doing this is because when we integrate for our total strain energy, so this integral out here now, this is with respect to the beam. So we actually have to have things in terms of displacement. So I'm going to come down here and I'm going to say my total strain energy is going to be the integral of our strain energy density. And now we're going over the beam itself. So we're going to go from x1 is equal to 0 to L. So if I were to run this, this is now our strain, total strain energy. So this is this integral right here. And that first integral that we did up here, so this SED, that was this right here. So we have two different integrals. So hopefully that makes sense to you guys. Again, we're not actually going to explore what happens to these equations when the stresses become nonlinear. This portion right here, it's kind of more complex. So I'm going to make a promise to you guys, because I don't want you guys stressing. When we get into these nonlinear equations, I'm not going to expect you to derive them. I'm not. So if I were to give you, let's say, a question like this on the final, all right, if I were to give you a question like this one on the final, I will make sure that it uses these exact formulas that we're covering in this example. All right, I will not give you a question out of the blue where you're expected to go manipulate those formulas in terms of these nonlinear equations, I promise. All right, I promise you that. That is my promise to you guys. If I were to give you a nonlinear question like this on the final, so just like this, I promise that it will abide by these rules right here. Or basically, I promise that it will be the same as the example. That's it. I promise. So that's my promise to you guys. Don't worry about all this, basically this crap. It's not fun to look at. I don't blame you guys. So that's going to be our total strain energy. So that's that first component right here. But now we also need the work done on the system. So I'm going to come down here and I'm going to put work. Now we know that W is going to be what? What do you guys think? Do you guys remember how to find the work done on a system? Who remembers the work done on a system? No one? You guys just trolling me? Yes, the internal is equal to the external, but that's basically this part right here. How do we find out what exactly W is equal to? Force times displacement, exactly. Force times displacement. So when we're dealing with this, we have an actual distributed load. If you guys go back to the notes, to deal with these distributed loads, we take our distributed load, multiply it by our displacement, and then integrate over the beam. So our work here is going to be the integral of our distributed load, which is going to be P, and then we're going to multiply this by our displacement, which is U approx, and we're integrating this over the length of the beam. So we're going to go from x1 is equal to 0 all the way until L. So if I were to run this, I now have what my work is equal to. So if I come down here, I can say, all right, well, now that I know my total strain energy and my work done on the system, I can calculate my potential energy. So I'm going to say my potential energy, PE, is going to be my total strain energy minus my work done on the system. Nice and easy. So if I were to run it, no problems at all. So now I got a question for you guys. We have our potential energy now, and as we can see, it's a function of A2. How do we solve for A2? How do we solve for A2? You guys are shy again. We're going to use the Newton-Raphson method. That's why we learned it today. So we're going to actually use the Newton-Raphson method. So what we're doing in the Newton-Raphson method is we're taking an equation and we're iterating values until we achieved our desired results. So what I'm going to do is I'm just going to create a section right here, Newton-Raphson method. But the first thing that we actually have to figure out is this. What is the equation that we're trying to solve? So for you guys in the chat now, what is the equation we're trying to solve? Exactly. Oswald is correct. We're taking the derivative of our potential energy with respect to A2. Now, when we take the derivative of our potential energy with respect to A2, what do we want this equation equal to? In other words, what is our desired value? Exactly, 0. So what we're doing the Newton-Raphson method that we did before, and before we had a desired value of, let's say, 3. But now, since we're minimizing this equation, we know that our desired value, or what we want this function to be equal to, is 0. So that's going to be one of the key things. So the first thing I like to do is I want to define what exactly our function is that we're trying to solve. Now, the common mistake everyone does is they say it's just equal to the potential energy. They set the potential energy equal to 0. That's a trap. You guys seen Star Wars, you know, it's a trap. There's your trap right there. When we're dealing with the Rayleigh-Ritz method, we want to minimize the potential energy. So our function is actually the derivative of the potential energy with respect to A2. And this is the equation right here that we want to set equal to 0. So if we're looking at our Newton-Raphson method, we had that big uppercase F, which we set as our desired values. Well, in this case, our desired value is going to be 0. Now, this is great because we have our function and we know what our desired value is. Therefore, we can do our nice Newton-Raphson method. Now, what I'm going to do to make my lives easier is I'm just going to create kind of a dummy variable, and I'm going to say A2. So this right here is our unknown function, A2. They're basically our unknowns. So what we're going to do is I'm going to create the loop for the Newton-Raphson method. I'm not going to loop it yet, but we're going to go through the Newton-Raphson method, and then after we know that that is good to go, then we're going to start looping it so it can do all of the iterations that we want. All right, so hopefully that makes sense to you guys. So before we go into the iterations, we actually have to define what something is. What is something we need to solve for that delta x that we have not defined yet? Let's see, did I leave the PowerPoint open? Oh, I did not. So let me pull it up. You guys can answer in chat. So this is a single variable case. So what is the one thing in this equation that we don't know yet? Because again, we're solving for delta x. So F we know is 0. Our function we know is going to be the derivative of that potential energy. So what is the one thing that we don't know yet? KT. Exactly. So we need to solve for KT. Now KT in a multivariable case is that matrix. But for a single variable case, it's nice and simple. KT is simply just the derivative of the function that we're interested in. So right here, this is why I defined my function right here, because what I can do is I can say KT is simply going to be the derivative of that function. So it's going to be the derivative of the function, and of course, it's going to be with respect to A2. So hopefully that makes sense to you guys. So now I have absolutely everything I need to have in order to start my iterations. So when I go through my iterations, and I'm going to actually pull up the PowerPoint. Where's the example? So now that I have this, this is my function, and I now have this, I can go to my iterations. So what I'm going to do is I'm going to have an initial guess, right? An initial guess. So this is going to be the first thing that we're going to scroll up, and we're going to say, all right, one of the parameters we need in our Newton-Raphson method is an initial guess. So what do you guys want to put it as? 0.01? Sound good to you guys? You guys want to do it as 1? Completely up to you guys. What do you guys want for an initial guess? 0? All right. Oops, wrong slide. Completely up to you guys. So now we have our initial guess, so we're good to go. Now we're going to go back to the PowerPoint and say, all right, after our initial guess, we evaluate our function as well as KT at that initial guess, right? Does that make sense? We have our initial guess, so then we evaluate our function as well as KT at that initial guess. That's all I'm going to do. So I'm going to come down here and I'm going to say, all right, well, now that I have everything, I'm going to evaluate our function at our current iteration. So I'm just going to call it function. We'll go INC, or we'll go iter. Sure, that works. A function at the iteration. So this is going to be equal to our function, specifically when A2 approaches xi. So this is going to be our initial guess. All I did was I'm taking our value of our initial guess and I'm substituting it into our function. And we're going to do the exact same thing for KT. So we're going to say KT at our current iteration is going to be equal to KT, specifically when A2 approaches our initial guess. Does that make sense to you guys, or is that a little bit too crazy? Hopefully that makes sense to you guys. Well, what exactly we did just there. What do you guys think? I need that confirmation, or else I'm going to get scared that you guys are lost. I got a yes. Private message, yes. Perfect. So now that we have both f of xi and kt, we said that we can actually solve for what our delta is. Delta x right here. And we have a nice formula right here. So what I'm going to do is I'm going to say, well, we can actually go to the more simplified formula right here. So in this case right here, what is f? What is f for our particular case? Zero. Exactly. It's going to be 0. So our delta x is actually just going to be negative f of x divided by kt. Nice and simple. So what I'm going to do is I'm going to, after I define this, I'm going to come down here and I'm going to say that delta is equal to -1 times our function at the iteration and then divided by kt of our iteration. Nice and simple. So then I'm going to come down here and say, all right, well, now that I know what delta is, I can find the next increment step, where xi is going to be equal to xi plus delta. So this right here is actually going to be our loop. So we're going to find the values of our function, and this matches the PowerPoint exactly. And I'll put the PowerPoint off to the side. I'll go here, I'll zoom in. This is exactly what we're doing. We have our initial guess. We evaluate both the function as well as kt in the loop. We figure out what our delta x is right here. And then we figure out what our next increment size is going to be. So from here to here, this is what we're going to loop. Now, this right here is good, but we also need to have, okay, I'm close enough. I need to back out. So what I'm going to do is I'm just going to comment the code really quick so you guys know exactly what's going on. So we're going to say calculate function and kt at current iteration. We're going to put right here where that we're solving for delta x. And then right here we are finding xi for next iteration. I don't know why, but I like to capitalize these things. I'm crazy. So hopefully that makes sense to you guys what we're doing in this loop. Now, another thing that we said that we had to do is we have to kind of judge when this convergence occurs. I don't want to keep looping if I'm already at my desired value, if that makes sense. I don't want to keep doing that. So what I need to do is I need to create some sort of failsafe that says when my tolerance is good enough, quit the loop, display my results. So what I'm going to do is we're going to come down here and we are going to create a section called break loop once convergence occurs. Now, when we're doing this, what we said is we base this based upon the error. Now, in this case, we're going to say that our error is simply going to be equal to, and I'm going to the formula right from the slides, it's going to be delta minus our initial value of x. So here's the problem, is this right here, this is our initial value for the next iteration. All right, it's not the initial value for this iteration. So what I need to do is I need to actually store the initial value for this iteration. So I'm going to go x initial, and it's currently equal to xi. So basically what I'm doing is I'm saving the initial value as this parameter right here before I change it for the next iteration. Hopefully that makes sense to you guys. Because when I'm calculating this error, this x right here, this xi, it should be 1. But if I were to leave it like this, it would use 5 instead of 1. So what we actually have to do is save that current value. So this is going to be my error, and we're going to make it in terms of percent. So all I'm going to do is I'm just going to times by 1,000. Times by 1,000. Now the question is, how do we compare this error? We're going to get our error here, and let's say that it's 20%. How do we know if 20% is good enough? Well, right now we don't. We need to specify a tolerance for our error. So what we're going to do is we're going to come up and we're going to say, you know what? Another parameter I need in this Newton-Raphson method, we need to actually specify what our tolerance is. So what I'm going to call this is I'm going to call this our error limit, and let's set it to, let's say, 0.5%. 0.5%. So that means that if our error is less than 0.5%, we're going to quit out of that loop. Make sense to you guys? Hopefully. So what I'm going to do is I'm going to come down here. I'm going to say, all right, well, now that we have our error, we can put in our statement so that if that error is reached, we quit our loop. So what I'm going to do is I'm going to use an if statement right here. And the first part is we have to set our condition. So we're going to say that if our error is less than or equal to our error limit, we can come down here and do everything that we want. But one thing that we actually have to do is we need to do absolute value of error. Because in our current state right now, we can have an error of negative 30%. Now, technically, that negative 30% is less than our error limit because it's a negative number. So we always have to make sure that we're doing the absolute value of our error. So if our error is less than our error limit, what I want to do is I'm going to put a message, and I'm going to say analysis converged. I even put an exclamation mark because we're so happy. Then what I'm going to do is I'm going to print, and I need to put one of those suppressors at the end. I'm going to go coefficient A2 is going to be equal to, and then what I'm going to do is I'm going to put what our coefficient of A2 is equal to. So now my question for you guys in the chat here is, if our analysis converged, what is A2 equal to? This is a good question. If our analysis has converged, what is A2 equal to? No one? It's going to be equal to xi. Xi is what we're iterating through. We're trying to iterate through xi, which is basically A2, until we achieve our value. So if our analysis has converged, then our value is actually equal to A2. Nice and simple. Make sense to you guys? All right, I guess this would be xi. That doesn't make sense, but this makes sense. If our analysis has converged, it means that A2 is equal to xi. What I'm also going to do is I'm going to print our error. So I'm going to go error is equal to error. And we're going to also error, comma, and I just want to specify that this is in a percentage. This will make more sense once we run the code, hopefully for you guys. You guys know what I'm doing so far, or have I lost all you guys? So again, good so far? Okay, if you guys are good, I'm good to go. So what I'm going to do also is I'm going to print a couple more things. Actually, I'm not going to print any more things. If it's converged, we know that A2 is equal to xi. So what I'm going to do is I'm also going to say that A2 is equal to xi, nice and simple. And I'm going to put convergence equals 1, which basically means that convergence is true. And you'll see why exactly I do that a little bit later. So I'm going to make this look a little bit nicer. And then the final thing, of course, we have to do is we need to break our loop. If I could spell break right. We need to break our loop. So this right here is our if statement right here. And it looks like I'm missing something. That's why. All right, so now this can come back. And then this can come back. Perfect. So this is our if statement, and this breaks our loop. So right now, Mathematica is thinking, what the hell are you doing, Clayton? You put a break loop statement even though you don't have a loop. So this is going to be one of the things that we have to define a little bit later. Well, actually, let's define it right now. So we know that we're going to want to do a loop. So what I'm going to do is I'm going to use a for loop. You guys can use any loop you want. If you guys want to do a while loop, go for it. That's the nice thing is you guys can pick anything that you want. So we're going to start at I equals 1. So this will be our first iteration. And then we're going to stop when I equals what? So this is one of the things that we also have to specify. We don't want to go forever. Because what happens if it doesn't converge? Then Mathematica is just going to try and recalculate the same crap over and over again. So what we actually should specify is a max number of iterations. A maximum number of iterations. So that if it's not converging, Mathematica says, okay, well, we're going to stop. It hasn't converged. No results. So max number of iterations, and we're just going to go I++. So once we do that, we can throw everything in here. Everything is going to stay the exact same, and it's just going to keep going down. Now this loop is going to keep on going until basically this occurs, or the max number of iterations has converged, or has occurred. So we're going to have an error message if max number of iterations reached. So what I'm going to do is I'm going to say, oh, hold on one second. If I, which is our current iteration, is equal to our max number of iterations, well, then we know that we have to print a message saying basically max number of iterations reached. So this just lets us know that the program quit. It reached the maximum number of iterations. It wasn't successful. Therefore, that's all it's going to do. Because what happens is if I don't include this message, I can run Mathematica and it'll just display nothing. And then everyone starts going, well, hold on one second. What happened? Did it converge? Did it not converge? Well, now this will let us know if it did not converge or if it did converge. But one thing that we have to keep in mind now is we define this maximum number of iterations. We actually need to define what it is. So we defined our initial guess. We defined our error limit. Now I'm going to come down and I'm going to define our maximum number of iterations. And usually you should start with just 1. If you don't start with just 1 and you do 20, and there's something wrong with the code, well then Mathematica is just going to take forever analyzing basically garbage. So usually you start with 1, see if everything's working the way you want it to work, and then you're good to go. So what I'm going to do is I'm actually going to run the code, and we have a problem right now, which is KT. So this is one of the problems that we had. So we divided by KT. Now what was wrong with KT? Our initial guess was 0. So this is one of the things where that engineering judgment has to come into play and say, well, you know what? It's equal to 0. That didn't quite work. Let's change it to 1. So now we changed it to 1. We had nothing displayed, nothing converged, but it says the max number of iterations has been reached. And that makes sense. We only did 1 iteration. Chances are it didn't converge. But one of the last things I want to add to this loop is just an updater. We knew that we did an iteration, but we have no information on this iteration at all. So what I'm actually going to do is I'm going to create another section just to track the results. So track results, so that you guys can see what exactly is happening at each iteration. So the first thing I'm going to put is I'm just going to specify what iteration we are on. So iteration, well, we know that we will always be kind of on our I iteration. Next thing I want to put is I want to put our current value of A2. So I'm going to say coefficient A2 is equal to, and we said that A2 is actually just going to be equal to xi for all of these iterations. And it stops when xi converged on that point. So A2 is going to be equal to xi, no problem at all. And then we should also specify what our error is. So we have a good idea of what exactly is happening. So we're going to say that our error at this, if you can spell it right, of course, our error is equal to our error. And another thing I like to do, because again, sometimes people forget, is I like to just put what the units would be. So our error is, of course, going to be in percentage. Now, just to make things a little bit nicer, I am just going to include this, which is basically just a blank line. And I'm just going to 3, 1, 2, 3, and this will make sense. So now if I were to run this code, we say that our first iteration, we have A2 is equal to 0.666 blah, 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 and our current error is around negative 33%. And this is why we had to do those absolute value signs in front of, where the heck was it? In front of our error. Because if we had negative 33%, this is technically less than 0.5% because it's negative. So this is why we always have to use those absolute values. So we said iteration 1, A2 is this, our error is this. Well, we didn't reach convergence and our max number of iterations has been reached. So from here we can say, all right, well, one iteration didn't work. What happens if we go back up here and say, you know what, instead of 1 iteration, let's do 3 iterations. Now we can see that iteration 2, we have coefficient A2 is 0.66. The error is still 33%. Then we did our second iteration, A2 is 0.44. Error is still around 33%. And the reason why the error isn't changing much is because we're dealing with these small decimal numbers. That's the reason why. After there, we go into 0.29. Error is still 33%. So after 3 iterations, nothing really has happened thus far. So now let's go to 10 iterations. We run this bad boy, and we can see that everything starts decreasing, and now our value is becoming smaller and smaller and smaller. Now again, because these are such small decimal numbers, the error isn't a very good measure because it seems like it's getting larger, but that's again just because things are getting so small. Now what I'm going to do is I'm going to do 20 iterations. Run this bad boy, we come down here, and as we can see, we got a message. Our analysis has actually converged. We can see that our coefficient of A2 is equal to negative 0.0096, and the error associated with this is negative 0.2%. So at this point, we are actually good to go. It was able to converge and find our value of A2. Now the question is, though, how do we know if this is a good value? Is there any technique to estimate good iteration numbers or time step? In these kind of problems, no, this is kind of just playing with it, but ABAQUS does. And we're going to discuss what exactly ABAQUS does here after. We're going to take a little bit of a break real quick soon, and I'm going to show you what exactly ABAQUS does, because there is techniques that ABAQUS uses. So now we are done our loop. Everything looked good. We were able to converge, and we stored A2. So what I'm going to do now is I'm just going to plot our results. So we're going to plot two things. We're going to plot, first of all, U exact, and we're going to plot U approx. And we're going to plot these over x1 from 0 to L. Come down here, and these are our results. So of course, it did actually a reasonable job. Now, we did our approximation function as a parabola. That's why it's kind of symmetric about the center there. But of course, our realistic approximation is kind of skewed a little bit to the right. So if we were to increase this to a cubic function, we would start to see it actually start to align more. But yeah, that's the Newton-Raphson method for this nonlinear analysis. So yep, that's it for this example now. And as I said, once we get back from our little bit of a break here, I'm going to show you guys what exactly ABAQUS does. So remember those step times that we talked about, we said we're going to discuss that later. Well, now we're going to discuss what exactly ABAQUS does in the finite element program. So we're going to take a break real quick, and let's say we'll come back at 10:23, and we're going to wrap up this lecture. So if you guys have any questions about this example, just type it in the chat and I will answer it as soon as I get back. Sorry for rushing off. I'll be honest, I really have to pee. So I'm going to go and do that, and I will see you guys after the break. All right, guys, I'm back. Don't worry, we're not going to start until 23. I'm just going to get ready for the next little portion here. So I can exit out of the PowerPoint, can exit out of the example. And what we should actually do really quick is we're going to just take a quick little peek at the assignment this week, because I know that everyone likes looking at the assignment and stuff like that. The assignment this week shouldn't be too bad. The example that we did was overkill. It was a lot harder than whatever the actual assignment is going to be, so don't worry about that. So assignment 6, and I'll zoom in a little bit. And yeah, at 23, or I guess in like less than a minute's time, we'll come back and we'll figure out what exactly is going on with this example. Voice is getting real sore. These 3-hour lectures are just, they're kind of brutal if I'm being honest on my voice. I can't talk for the rest of the day after. All right, it's 23. That awkward moment of silence is now gone, and we can kind of get back to things. So assignment 6, it's not too bad. It's two questions. And I still call it isoparametric elements, but it's basically a combination of that as well as the Newton-Raphson method. The Newton-Raphson method, what we learned today, is solely contained in question number 2. And it's actually very simple. We give you guys a nonlinear equation, so single variable. We have one equation, one unknown, which is strain. And basically, we're just going to use the Newton-Raphson method to find a desired 4,000 units of stress, the modified Newton-Raphson to find a desired value of 4,000 units. And then we are going to do the exact same thing for 6,000 units. So when it comes to question number 2, the Newton-Raphson method, it should be a piece of cake. Again, everything that we did with potential energy just now, that was overkill. We're not going that crazy. You guys have one equation. You guys know your desired values in each part of the question. You guys basically just do the Newton-Raphson method to figure out what is the strain going to be to achieve those values of stress. So question number 2, is there any questions about that, or are you guys thinking, yeah, this isn't too bad for question number 2? Again, single variable. Hopefully not too bad. All right, well, if you guys disagree later on, let me know. So if we look at question number 1, this kind of goes back to last week with those isoparametric elements. So what we're basically going to do is we're going to take a 4-node quadrilateral isoparametric element, and it gives us the material properties as well as the coordinate points. The first question is find the stiffness of the element using the full Gauss integration scheme. You guys have your code for this already from the last assignment. This is going to be a piece of cake. Now, part B says find the stiffness of the element, or the stiffness matrix of the element, using ABAQUS. My question to you guys is, you guys know how to find the stiffness matrix of an element in ABAQUS? What do you guys think? How to find the stiffness matrix of an element in ABAQUS. That's where the trick comes in. Radio silence? Don't know? All right, well, I'll show you guys. So that's not going to be too bad. Nice and easy. And then part C is just compare the two results. Part D says, assuming nodes 1 and 2 are fixed, find the displacements at nodes 3 and 4. Under a vertical gravity load, if the density of the material is 2,400 kilograms per meters cubed and gravity is 9.81 meters per second squared. Nice and easy. You guys know the formula to figure out those nodal displacements. You guys know the stiffness matrix from part A. You guys just solve the equation. K times U is equal to F. Nice and simple. Using the loading defined in part D, determine the stresses and the strains at the integration points. Again, this is easy because from part D, you now know the nodal displacements. With those nodal displacements, you guys can find the stresses and the strains. And then compare the FEA results in part D and E with hand calculations. So these two are going to be done in ABAQUS. You're going to do the elements in ABAQUS, and then you're going to redo it with hand calculations and then just compare the two results. So it shouldn't be too bad. The only problem that I can see you guys having is that stiffness matrix in ABAQUS. So we're going to actually look at that right now. So I'm going to share my screen over onto the small screen right here. Oops. And this is what's going to happen. What we're going to do is we are going to define our element in ABAQUS. So something like this. And we know that our element is going to have those 4 nodes. So we're going to have a node here, we're going to have a node here, and we're going to have a node here and a node here. Now our stiffness matrix can be written in the form where we have Kij, Kij, right? It has component I and a component J. Now, what this is actually equal to is the force at node I after a unit displacement. So a unit displacement at node J. So this is what you guys are going to do in ABAQUS. You're going to create your elements, and you guys are going to fix all of those nodes. You're going to set the displacement to all of those nodes is equal to 0. Now let's say that I wanted K, we'll go 1, 3. All right, if I wanted to know what K13 is in that matrix, what I'm going to do is I'm going to move entry 3 here, which is going to be this right here. So this would be my DOF3. I'm going to move this by a value of 1, and then I'm simply going to measure the reaction force, the horizontal reaction force at DOF1. Does that make sense to you guys? What do you guys think? Does that make sense? Radio silence. It's basically just follow that formula right there. No one's brave. No one wants to talk. If I wanted, let's say, K24. Remember that these right here, these are the degrees of freedom, not the elements. Degrees of freedom. So what I would do here is I would move degree of freedom 4 by 1 unit. So in this case, I'm moving this up by 1 unit. And then I'm measuring the reaction force at degree of freedom 2. Degree of freedom 2 is the vertical reaction force at node 1. So what I recommend doing is just follow that same formula, but over here, just make sure that you know where the degrees of freedom are. So if we had 4 nodes, 1 at each corner, and I'll do this in a different color to make it stand out a little bit, we know we have degree of freedom 1, degree of freedom 2, degree of freedom 3, 4, 5, 6, 7, and 8. How's that look? Look a little bit better? All you guys are doing is displacing one of those degrees of freedom and measuring the reaction force at all the other degrees of freedom. That's it. That's all. Nice and simple, or at least hopefully. I'm sure I'll get a lot of questions. If you guys don't know and require more clarification, just ask me. I'm happy to help with whatever you guys want. Now we're going to get into something a little bit different. We're going to discuss what exactly ABAQUS does to account for these geometric nonlinearities and what it does for that technique of good iterations. So what we're going to do is we're going to say that we have a load displacement response. So this is going to be our load P, and this is going to be our displacement delta. And we're going to say that it's actually something like this, okay? So a nonlinear response. This is what ABAQUS does. So remember that in a linear analysis, everything is always based on that initial reference configuration. And we said, because of geometric nonlinearities, that's actually a problem. Because if something is really deformed and we're integrating with respect to that nice undeformed shape, well, of course, there's going to be some error. So what ABAQUS does is says, you know what? If you guys want a value that's, say, right here, that's the value that we're interested in. And actually, I'll just put a little line right here. This is the value that we're interested in. Instead of going from 0 all the way until that point, we're actually going to split it up into a number of intervals. So instead of going right from 0 to that point right here, what ABAQUS does is it's going to say, you know what, I'm going to figure it out here, 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 and here. And actually, you know what, it might even do it even a bit smaller when it gets more nonlinear. So this is what we're doing. So what happens is to get to this point right here, everything is based on this configuration right here. Then once we get to this point, this becomes the new reference configuration, and we try and get to this point over here, and then so on. So then this becomes the new reference configuration, and then we go to this point here. So does that make sense on how ABAQUS starts to account for these geometric nonlinearities? Besides buckling, we'll talk about that a little bit later. But does that make a little bit more sense to you guys on what's going on? Thumbs up, thumbs down. Clayton, you've completely lost me. Something? You guys are so shy. Nothing? Nothing? Completely lost you guys? I don't know what to say. I can't tell if you guys are actually lost or just trolling me. You guys are probably all laughing at me. Not sure yet? All right, so what we're going to do is we're going to look at the same curve and we're going to figure out about the ABAQUS solution technique. So yeah, we're going to talk about this a little bit more. So let's say that again, we go back to our curve. So what ABAQUS does is it tries to figure out how do we get to this point in a reasonable manner. So what ABAQUS is going to do, and I'm going to show you guys this, is it's going to split this up into steps. We said instead of starting from right here and going right to the end, it's going to go right here. That's going to have our first point. And what happens is to get from there to there, it actually does the Newton-Raphson method. So if I were to put a line here, it's going to basically do the Newton-Raphson method all the way until it reaches that point. Okay, so we said that this right here, this is the NR method. Now what happens is ABAQUS will track how many iterations it requires to go from this bottom point to this point I+1. Now the golden number, the number that's usually pretty good, is around 6. If it's around 6, then the increment right here will be about the exact same. The exact same. So let's say that this is equal to 1. Well, then if it does it at around 6, well, then the next increment will be the exact same. So it'll go up by 1 again and it'll go to 2. Now let's say that it does this and it is actually able to kind of get to there right away, 1 increment. Then ABAQUS will say, well, you know what, if it's only taking 1 increment, instead of 2, let's try and go all the way to 4. So what happens is at 4, ABAQUS will do more iterations using the Newton-Raphson method to get to 4. But let's say in this case, it took like 20 iterations. 20 iterations. Then ABAQUS says, well, you know what, that step was a bit too much. So instead of going to 4, I'm just going to go back to steps of 1. And it's slowly going to get all the way to this point. So from here, it's going to do the Newton-Raphson method again and again and again. Hopefully that makes a little bit more sense to you guys. But the thing I'm going to show you guys right now is we're going to define what these steps are. So as you're going to see, ABAQUS has an automatic step time. You guys can specify the initial step as well as the maximum step you guys want, but ABAQUS has kind of an automatic solver to try and figure out what these steps are. Okay. Now, another thing that could happen too is we can do the Newton-Raphson method and it doesn't converge. Does not converge. Well, instead of trying to go to this point here, ABAQUS will retry, but it's going to pick a lower point. Something like that. So I'm going to show you guys what exactly is going on. I think it'll be easier if we just throw up ABAQUS and we can have some fun with it. So we're going to go into ABAQUS. I'm going to switch my screen over to screen 1. I'm going to modify the display so you guys can see ABAQUS's little buttons clearly. Do this. Throw an ABAQUS over here. Go to display. And I'm going to go to this monitor right here. We are going to make it, wait for everything to kind of settle down. So how's that? Is the screen size pretty good? You guys can see all the buttons, the text, stuff like that. All right, I got a yes. So what I'm going to do is I'm just going to create a simple beam. Let's say the exact same beam as in the assignment. And naturally, since I have so many different monitors, I have no idea where the text box appears. So, oh, where the heck is it? Hold on, guys. I just got to find out where the text box is. It appeared in one of the other monitors, which I have no idea where it is. So let me just try exiting out of this. I'm going to exit out of a bunch of other stuff that I have popped on. Perfect. So now I'm going to reopen ABAQUS, and we're going to try round 2. ABAQUS is very much trial and error. There we go. Pop this back over to the other side. Move this up. And let's just see. Part creation box. Okay, I found it now. So now we have our parts. I'm not going to label it anything special. We're just going to do exactly the same as what we were doing in the assignment. So we're going to create a rectangle. Nice and simple. Done. We have our beam. We're going to go to properties. I'll put this over here too. We're just going to keep it elastic for now. Again, we're going to keep it the exact same as the example. So I think this was like 10,000, 0.3. Create a section. Everything's popping up on the other screen. So I got to drag it over. Assign the section to the beam. Again, I'm going really fast throughout this because you guys are smart. I'm going to bring it into our assembly tab, just like this. And then once we get to the step tab, this is where we start accounting for those geometric nonlinearities. So the first thing that we're going to do is when we create our step, the first part is this. It says, we want a static step. We get this menu. So to account for these geometric nonlinearities, we always switch this to on. Now, when you guys are using a finite element program and you guys are worried about geometric nonlinearities in ABAQUS, it's all you need to do is switch this to on. That's it. That's all. It'll take care of the geometric nonlinearities. But one of the things I want to talk to you guys about is step. So if we go to incrementation, we can actually define the step size. So for instance, if I wanted to go from 0 kilonewtons to 1 kilonewton, I can actually define the step size. And this is going to be a percentage of the actual time. So if we come back here, we see that our time period is equal to 1. This is kind of a pseudo time period. It's a fake time period because we're dealing with static steps. Now, what incrementation means is this is going to be how much of time you want to do per step. So if my time period is equal to 1, and it's saying initially I want to apply 1 period of time, well, then it's going to try and go from 0 to 100% in 1 step. 0 to 100% in one step. Now what I can do is I can change this to 0.1. So instead of going right from 0 to 1 kilonewton, this will go from 0 to 0.1 kilonewtons to 0.2 kilonewtons. It'll take step sizes of basically 10% to try and get there. So hopefully that makes sense. Now this is actually nice for us because what ABAQUS does at each one of these step sizes is it actually records the data. So before in your guys' assignment, if you guys jumped from 0 to 100%, you guys will have the beam at 0 and you guys will have the beam at 100%. But what this will do is this will actually capture the beam as it starts to deform at different values of load. So what I'm going to do is I'm going to put this as 0.1 and I'm going to show you guys what exactly this means. So when I go down to my load boundary conditions, again, they're popping up on the other side. I'm going to put my displacement in the initial step over here. It's they're all appearing behind the Zoom chat, so it's kind of hard to see. Perfect. And I'm going to apply my load right here in step 1. This one right here. -1. So what I'm going to do is I'm going to say, all right, good. I'm going to go to the mesh size. Now, another thing I want to show you guys too, and I realized I didn't show you guys this, is how do you do a triangular mesh? Well, to do a triangular mesh, you go to this button right here, Assign Mesh Controls. So by default, ABAQUS will have it so that it's doing quadrilateral meshes. So if I click this screen pops up, and it says Quad Dominated. So if I were to go Try, which goes to triangular, and I click OK, if I were to mesh this beam, we can see that we now have triangular elements. So that's how you guys do it if you guys want triangular elements. It's really up to you guys. So what we're going to do though, and this is kind of the whole purpose, is we're going to create a job and we're going to see what exactly is happening. So I'm going to go OK, and I'm going to submit this job. So we got everything that we need, it's submitted, but we're going to monitor this job so we can see what exactly ABAQUS is doing in the background. So I right click and go monitor, and you guys are given this screen right here. And these are what's actually going on when in terms of incrementation. So once it's done, it's going to start running, and then we're going to get all these popping up. So I did it really fast because it's almost a linear analysis. But this is what happened. We have step 1, so these will always be step 1 because step 1 was just loading the beam. And then we have a bunch of different increments. Now, these are the attempts. So what's going to happen is, again, it's trying to go from 0 kilonewtons to 0.1 kilonewtons. And sometimes it doesn't actually reach it. It diverges. So if that's the case, instead of 1, you guys would get 1U, which means that it was unsuccessful, that's the U, in getting to that attempt. But in attempt 1, it was able to succeed. And we can come over here and we can see what exactly happened. So basically, we went from 0, so 0 load, to 10% of the load. So we went from 0 kilonewtons to 0.1 kilonewtons, and it was no problem. These total iterations, this is the Newton-Raphson method. This is how many total iterations it took, the Newton-Raphson method, to go from 0 kilonewtons to 0.1 kilonewtons. Now, it says, okay, good. Now we're going to move on to the next step. In the next step, it wants to go from 0.1 kilonewtons now to 0.2 kilonewtons. How many iteration attempts did it take? Well, it only took 1. So now ABAQUS is saying, under these steps, 0.1, everything is going smooth. There's nothing going on that's too crazy. Nothing's diverging, anything like that. So instead of going up by 0.1, I'm going to go up by 0.15. So this is that increment over here. And then it does it, and it's successful. It only took 1 Newton-Raphson method iteration to get over there. So it says, okay, well, if this is going so well, instead of going up by 0.1, I'm going to go up by 0.225 kilonewtons. So it's saying, okay, well, that also worked well. So then I'm going to go up by 0.33. So this is ABAQUS's automatic sensor to try and figure out, okay, if the incrementations are going well in the Newton-Raphson method, I can try increasing that step size. Does that make sense to you guys? What do you guys think? Does that make sense to you guys? If ABAQUS is figuring out that the Newton-Raphson iterations are going good, it's not diverging, then it'll start increasing the load step sizes. And the opposite is true. So what happens in ABAQUS is that it attempts something, and let's say that it is unsuccessful. Let's say that going from 0 to 0.1, it was unsuccessful. It diverged. What happens is ABAQUS will decrease the step size. So instead of going to 0.1, it might go to 0.05 and try again. And it's going to keep trying. Now what happens is if ABAQUS has five unsuccessful increments in a row, it'll quit the analysis. ABAQUS will say that this diverged, we're quitting. And this is something that you're going to see a lot when we start getting into the plastic analysis in the next lecture, is it's going to start quitting. But what's nice though is this, is if we look here, we now have data on the beam for all these different loads. So if I were to go check my results, when you guys click this, it'll automatically go to the kind of the end right here, our last time step. But what I can do is I can actually look. I can go next right here, and I can see the beam under 0.1 kilonewtons. I can go next. I can see the beam under 0.2 kilonewtons. I can go on, and I can see the beam under 0.35. So every time it does one of those successful steps, it actually records the data, and you guys can see the beam as it deflects. It's not just here's the initial, here's the final. You guys can start seeing what happens in between. Now what happens is ABAQUS said, you know what? I had a lot of successful increments, so I started increasing that step size. But what happens if you say, well, you know what, ABAQUS, I didn't want you to do that. I wanted you to keep it at 10% maximum. So in our step here, if I were to scroll up to our step, what I can do is I can edit the step, and under incrementation, I can specify the maximum step size as well. So if I were to set this as 0.1 and go OK, I can come down here, resubmit the job, and once it does, we're going to monitor it. Takes a little while, or unless something's hidden. Oh yeah, it said, do you want to overwrite? But it was hidden by Zoom chat, so I couldn't see it. So I click yes, then it goes submitted. We're going to monitor this bad boy as well. And as we're going to see, once it starts running, it's all just going to kind of appear. And now, as we can see, it capped that maximum at 10%, basically. Does that make sense to you guys, hopefully? So I got a good question that says, what is the variable that ABAQUS is trying to converge? That comes from the PowerPoint. So what it's actually trying to do is it's converging force equilibrium. So it depends on if we're doing force control or displacement control. That's going to be what it's going to do. Basically, if it's force control, we know what our applied forces are, which are going to be our desired values. And what we do is we iterate through the displacements until our internal stresses are equal to our external stresses. Or in other words, our whole section is in equilibrium. That makes sense? Perfect. All right, good. It's just trying to keep the section in equilibrium. That's it. So now what I'm going to do really quick is I'm going to just reiterate one last thing. Is these increment sizes, these are increments of the time. All right, increments of the time. So by default, our ABAQUS time will always be set to 1. So these increments are always the increments of the time. So if I were to keep the increments at 0.1, this is always going to be 10% of the time. So our loads are going to always go up by 10%. Now, if I were to place a load on the beam of 200 kilonewtons, what this means is that our step size is still 10%. So each increment will be 10%. So of my 200 kilonewtons, 10% is 20. So it's going to go 20 kilonewtons, 40 kilonewtons, 60 kilonewtons, etc., etc. So that's one of the last things I really want to make clear when we're dealing with this incrementation. This is going to be something that we're going to play around a lot with when we start dealing with plasticity, because it's going to become quite critical to you guys. Does that make sense? Hopefully. I'm going to go over to the other screen really quick just to really show you guys what this increment size means, because it's something that's kind of difficult to understand, but once you guys get it, it'll be good to go. So I'm going to go back to this thing, whip out the drawing board. So what we're going to do is if we had our total time at 1, then it doesn't matter if we're going to have load 1 and we're going to have load 2. Now in load 2, we are going up to, let's say, 100 kilonewtons. And in load 1, we are going up to 10 kilonewtons. Okay? Did I share the screen right? Can you guys see this? So in both cases, we set our time is equal to 1. And we put our step size is equal to 0.01. So what this means is that if we're looking at this, this means that our load increment is always going to be 10%. So in this case right here, we are going to go from 1 to 2 to 3, all the way up until we reach 10. So this right here will have a total of 10 steps. We're going to go 1, 2, 3, 4, 5, all the way to 10. Now in this one, our load size still goes up by 10%. So even though the only thing we change is the load, this will now be 10. This will now be 20, 30, and this will go all the way up until it reaches 100. Does that make sense to you guys? This right here is the step. So if we were to do the load percent, it's simply going to be our step size divided by our time. So in this case, we have 0.1 divided by 1, which is 0.1, which means that our load is going to be applied in 10% increments all the time in ABAQUS. And this is something we play with. Again, if ABAQUS is not converging, it'll start lowering that step size. Or if ABAQUS is converging rather easily, it'll start increasing that step size. And yeah, that's it for step size. So just a little recap real quick before I let you go. Nonlinear geometry, this is what gets you in the green zone for ABAQUS. All you have to do is click this equal to on. That's it. Nice and easy. When we start talking about plasticity, things get a little bit more complex, but nonlinear geometry, that's equal to on. So if you guys are a little bit, you know what, Clayton, I'm still not 100% convinced, don't worry. The next lecture is basically going to be all ABAQUS. I'm going to show you guys exactly how to conduct one of these nonlinear analysis in ABAQUS, and we're going to talk about the influence of step size. We're going to talk about everything else. So this was kind of a warm-up, if you will. So don't think that this is the final, you should know this, you're good to go. This is kind of the warm-up. Next lecture, I'll really show you guys what exactly is happening. So that's it for today. Is there any questions, or how are you guys feeling? I was probably a little bit confusing today. Nonlinear analysis is, it's not the most fun thing in the world. But yeah, let me know if you guys have any questions, and yeah. If there are no questions and you guys are heading out right now, then I just want to say have a great day. I know it's a little bit colder, but it's getting warmer, so yeah, nice. Okay, so yeah, that's a great question. So in the assignment, I said hand calculations. This can be in Mathematica. Yeah, please don't do this by actual pen and paper. That would be absolutely brutal. Hand calculations basically means just with your own theory. If you guys want to use MATLAB, go ahead and use MATLAB. Please don't do it by hand. You make me cry. Yeah, no, I'm not that mean. Well, not yet. I find professors tend to get meaner as they age, so we'll have to see. So another question is, where can we find the stiffness matrix in ABAQUS? Well, if you guys have nothing better to do, I will show you guys. So let's go into ABAQUS, and let's show you guys exactly how to get the entries of the stiffness matrix. Sound good? This will be extra. So if you guys want to know how to do it, you guys go ahead. Think of this as kind of an extra little fun time. So what I'm going to do is I'm just going to create an element in ABAQUS. So you guys know parts. Actually, I kind of like this where I'm not restricted by time and I can just show you guys what I want to show you. So the first part is to create our element. So we're just going to name it element. And we know it's going to be, oh, not sharing. Good call. Good to go. Perfect, perfect. So we're going to create our part, and all I did was I called it element, and it's going to be 2D planar, deformable shell, same thing as before. So I'm going to go approximate size is 5 just because I don't want the grid so big. Again, that plays no real impact. And I'm just going to make a square element. So I'm going to go to this create rectangle, and I'm going to have 0, 0 as the first corner, and then I'm going to go up to just 1, 1. So again, all I did was I just created a nice square element. I'm going to go done. This is going to be my element right here. So what I'm going to do is I'm going to go into properties, and I'm going to have to define some material properties for this bad boy. But of course, we're just going to keep it elastic. So I'm just going to go elastic. And I'm just going to say that the Young's modulus is 10,000. I'm not sure what the assignment is. And we're going to go 0.3 for Poisson's ratio. So just typical values, nothing too special. And then I'm going to assign that section or that element property, or sorry, the material property into the element. The first thing I do is I create a section. I'm just going to call this my element section. Continue. It's going to be the elastic material recreated. I'm going to go OK. So this creates the section, but now I'm going to apply that section I created into our element. So I'm going to click OK. It says section element, which we created, good. And again, you guys will know if you're in the green, if this turns green. That kind of sounds funny. You're in the green if it turns green, but that's all you do. If this is the case, you guys are good to go. So after property, I go down to assembly. So again, this is what ABAQUS is really analyzing, this space right here. And right now there is no space. So we're going to bring in our element. So I'm going to import that instance. I'm going to go OK. And now I have my element in the modeling space. I'm going to come down here and I'm going to go into step, and I'm going to create my step where I apply my displacements. So the key to finding the element stiffness is we're going to apply displacements to this element. So I'm going to go apply displacements. It's going to be a static step. And again, the only thing that I'm going to do is I'm going to turn on this nonlinear geometry. The step size incrementation, again, that's a taste of what we're doing later on. For this particular question, it's a linear analysis, so we don't need to play with this whatsoever. So we're just going to go OK. And then I can go down into my loads. So this is where it becomes a little bit tricky, but it's actually kind of simple. We're going to go down to loads, and we're going to create basically 4 boundary conditions. So what I'm going to do is I'm going to go boundary condition, and I'm going to call this one node 1. It's going to be a displacement boundary condition. So what I'm going to do is I'm going to click OK. I'm going to select node 1 here at the corner, go done, and I'm going to restrain it in both the vertical and the horizontal directions. I'm going to create, and I have my list here, I'm going to create another boundary condition, and I'm going to call this one node 2. Again, displacement rotation. I'm going to select node 2, click done, and then I'm going to set these as both 0 as well. And I'm going to repeat this process for all of the nodes of my element. So I'm going to have node 3 now, come up here, click, done, 0, 0. And finally, I'm going to do the same thing for node 4. Click continue. I'm going to click here. I'm going to go done, 0, 0. Good. So this is basically the situation you guys want to be in before you start analyzing what the values are going to be. But of course, you guys have to do a mesh as well. So I'm just going to do my mesh really quick. I want to make sure that this is just a single element. So I'm going to make sure that my mesh size is 1. Apply it. Good. And then I can mesh the part. But another thing too is we have to make sure that we are not using reduced integration. So I'm going to disable reduced integration. Then I'm going to mesh my element. So as we can see, we just have one single element. All right. So remember that our element stiffness matrix entries, Kij, where what they're equal to is the force at DOF I after unit displacement at DOF 3. And I know that sounds really, really crazy, but this is what we're going to do is we're going to start playing around with these boundary conditions. So if I want the first row, or sorry, the first column of my matrix, it's always going to be Ki and then 1, because the first row is always going to be, or sorry, column is going to be 1. So remember that Kij, actually, let me just write this on words so you guys can see. I don't want to switch screens because that'll just get into be annoying for us. So let's just put this up to 18. So Kij is equal to, the force at DOF I after a unit displacement at DOF J. So for instance, if I wanted that first column of my matrix, so if I wanted KI1, what I'm doing here is I'm apply a unit displacement at DOFJ, so at DOF1, and then measure the forces at DOF I. Does that make sense to you guys? So all I'm going to do here, if I want that first column, is I'm going to have a unit displacement at DOF1. So I'm going to come down here. DOF1 is the horizontal displacement of my node 1. So I'm just going to, I'm just going to edit node 1. And instead of having it 0, I'm going to put a unit displacement at node 1. So if I were to come down to my job and I were to run it, it already exists. So this might lead to some errors. I might have to name it something unique, but we'll see. Running. So I'm going to look at my results, and as expected, we have something like this. Now, of course, this looks like complete crap. But basically what's going to happen is this is only like this because I put it as 1, 1. In your guys' assignment, the element's bigger than that, so it's not going to have this weird shape. But basically, after we do this, all we're going to do is look at the reaction forces at each one of the nodes. So it's kind of hard because I don't have my probe value, but you are just basically going to probe the 4 nodes, and whatever those reaction forces are, that is your stiffness entry, whatever. So for instance, this node right here, node 3. Node 3 has DOFs 5 and 6. So if I were to probe the horizontal displacement at node 3, I can get my stiffness entry 5-1 and 6-1. Does that make sense? 5-1 is going to be the horizontal displacement at node 3, and 6-1 is going to be the vertical displacement at node 3, or the vertical reaction. Does that make sense to you guys? What about K11? It'd just be the horizontal force at node 1. Yeah, I didn't think about it, but I shouldn't have put it as a 1, 1 element because then I can't really measure it. And I guess I can't anyways because of the probe value, but that's all you guys do. Apply your unit displacement, probe the 4 nodes for your 8 values, move on to the next one. So instead of, if I want the second column now, well, I know that the second degree of freedom is the vertical degree of freedom at node 1. So I'm going to set this one equal to 0. Then I'm going to set this one equal to 1. Redo the analysis. And you kind of just do that 8 times. But keep in mind, and this is one of the things too, your matrix is symmetric, right? The stiffness matrix is going to be symmetric. So once you're getting into the later stages, you guys don't actually have to look at all 4 of the nodes. You guys just have to make sure that you guys are getting a nice diagonal part of the matrix, and then the other part you just say is symmetric. Nice and easy. So please don't do more work than you should. But yeah, that's it. No, perfect. I'm glad that you guys liked it. I like that I can teach you guys without feeling time constraints. It gets hard to rush at the end. Anything else you guys want to see really quick in ABAQUS, or you guys just want to leave? No problem, guys. Yeah, I'm here for you guys. Let me know. Anything else you guys want to see in ABAQUS? I can show you right now if you want. As long as it's not too crazy, I guess. And if you guys are heading out, have a good day. Don't forget that. Enjoy your day. Enjoy life. It's nice. Life is nice. No problem, guys. Have a wonderful day. Again, feel free to ask whatever you guys want. I'm here to help you guys. Students don't realize that enough, is that this is for you guys. Yeah, no problem.